When we think of our senses, the usual five tend to rise to the surface, yet quietly, without ever demanding much of our conscious attention. Another sense is at work. It is the sense of balance, the ability to know where our body is in space, to move without toppling, to lie down and drift into sleep without fear of falling. This quiet sense is guided by the vestibular system, a hidden set of structures deep within the ear. Tonight, as you rest and let your breathing slow, we will begin a gentle journey into this remarkable but often overlooked system, exploring its beauty and function with calm and steady pacing, allowing the knowledge itself to become a soft rhythm guiding you toward sleep. The vestibular system resides in the inner ear, a place already famous for its role in hearing. But in truth, it does far more than transform sound into signals for the brain. Just behind the protective layers of bone and tissue lies a set of winding passages, almost like a miniature labyrinth. These passages are filled with fluid, with delicate hair-like sensors, and with tiny crystals that respond to gravity and movement. The entire design is like a hidden compass, always working, always helping you remain steady. Even when you close your eyes, when sight and external reference points disappear, this inner sense continues to orient you, telling you which way is up, which way is forward, and when you are still or in motion. To imagine the vestibular system, picture a tranquil pool of water. Imagine a gentle ripple passing across its surface. That ripple is like movement through space, and the receptors within the inner ear sense it, translating its direction, its speed, and its force into signals that your brain can understand. These signals then merge with those from your muscles, your joints, and your vision, creating a unified awareness of balance. It is not loud, it is not demanding, it is steady, quiet, and continuous. Without it, the simplest of tasks would be overwhelming. Walking across a room, reaching for a glass of water, or even resting in bed would be uncertain. With it, life flows more smoothly. The beauty of the vestibular system is that you rarely notice it when it works correctly. Its very success lies in its invisibility. Only when it falters do we become aware of its presence. A sudden spell of dizziness, a brief wave of vertigo, or the unsteadiness of stepping off a spinning ride at a carnival. All these are reminders of the normally hidden system, but when it is in harmony, it is like a constant background hum, a silent stabilizer, ensuring that life unfolds with grace. This sense of balance is not only physical but also deeply linked to comfort and calm. To be well balanced is to feel safe, secure, and steady. Even in language, we associate balance with peace. We speak of a balanced life, a balanced state of mind. In many cultures, balance is synonymous with health itself. This connection is not accidental. The vestibular system roots us in the physical world, anchoring our movements and letting us trust that the ground beneath us is stable. Without that trust, unease would follow us everywhere. With it, we can relax and let go, knowing our body will remain steady. As you lie here, you might gently notice the feeling of your head against the pillow. Notice the sensation of stillness, the lack of sway, the ease of simply being at rest. This comfort comes from the vestibular system silently reporting that all is well. Your body is horizontal, the world around you is still, and there is no imbalance to correct. It is this continuous feedback that allows sleep to arrive without disorientation. Even in dreams, the vestibular system whispers, guiding the illusions of movement we experience while slumbering, giving our dreams a sense of space and motion. Scientists sometimes call the vestibular system the sixth sense, though in truth it could be called the first, for it is one of the earliest to develop. In the womb, long before the eyes open, before the ears detect music or voices, the vestibular system is already forming. The developing infant feels the sways and turns of the mother's movements, rocked gently with each step. This may explain why rocking a baby has such a soothing effect, why gentle rhythmic motion lulls us towards sleep. The vestibular system is ancient, both in evolutionary history and in our own lives. It links us to the rhythms of movement, to the feeling of orientation, to the deep comfort of being cradled. Across the animal kingdom, this system takes many forms, but always carries the same purpose: to maintain stability and awareness of position. Birds rely on it to soar and dive with precision. Fish depend on it to navigate in water, sensing currents and orientation in the depths. Cats, known for their uncanny ability to land on their feet, are guided by a vestibular system that instantly tells them which way is down, allowing their body to twist mid-air in perfect alignment. We humans share this ancient mechanism, adapted to our upright posture, to walking on 2 feet, and to exploring the world with a steady gaze. The inner ear, where the vestibular system resides, is a place of exquisite design. Its tiny structures are smaller than a grain of rice, yet their role is vast. These chambers and canals never stop working. Whether you are awake or asleep, active or resting, even the simple act of turning your head on the pillow is registered instantly. The inner ear notes the movement, informs the brain, and ensures that your sense of the world remains stable. That is why, when you close your eyes and drift toward sleep, you do not feel lost in darkness. You feel anchored, grounded, gently supported by a system that never stops attending to your balance. As we begin this long exploration, it is helpful to recognize how balance shapes our lives beyond the physical. When we speak of balance, we are often referring not only to body but to mind, a balanced thought process, a balanced lifestyle, a balanced heart. All of these metaphors trace back to the same sensation: the comfort of steady grounding, of not tipping too far in one direction. The vestibular system is the physical mirror of this universal idea, a reminder that stability underlies both movement and rest. In the hours ahead, we will journey through the details of this system, from its structures and their delicate workings to the way it connects with other senses, with our daily experiences, and even with our dreams. But for now, as this first part draws to a close, let your body rest in awareness of balance. Feel the calm of stillness, the reassurance of equilibrium, and the quiet presence of this hidden sense. Just as the earth turns smoothly on its axis, just as waves roll gently to shore, so too does your inner balance continue its work. Steady, rhythmic, and unbroken, the vestibular system will remain with you as you drift deeper into calm, always steady, always reliable, and always silent. In this way, it is not just a part of anatomy, but a companion to rest itself, guiding you towards stillness, guiding you towards sleep. 2. Why balance matters. The sense of balance is something so ordinary, so constant, that we rarely give it thought. Yet it is one of the great quiet gifts of the human body. Imagine for a moment how many movements you make in the course of a single day. Rising from bed, placing one foot in front of the other, reaching for an object on a shelf, turning your head when you hear a sound, bending down to tie your shoes, or lying back to rest. Each one of these acts requires balance, not just in the muscles that hold you steady, but in the invisible signals that flow from the inner ear to the brain. Without those signals, these simple acts would become uncertain, and the world would tilt and spin in unpredictable ways. Balance allows us to move through life with ease, conserving energy and maintaining comfort. Think of walking across a room. With every step, your body sways slightly, your head shifts, your arms swing gently. The vestibular system detects each small change and guides the brain to make tiny corrections. Muscles contract here, relax there, joints adjust ever so slightly, and posture remains upright. You do not think about these corrections, and you do not feel the millions of adjustments taking place, but they are happening constantly. In this way, balance is like a silent partner, always at your side, making life smoother and movement graceful. Even in stillness, balance matters. As you lie in bed now, breathing slowly, your body remains aware of its orientation. The vestibular system is quietly confirming that you are horizontal, safe, and secure. This is why stillness feels calm rather than unsettling. Imagine lying down without that inner confirmation. You would feel adrift, uncertain of direction, as if floating without anchor. Instead, the vestibular system assures you that you are steady. It communicates this to your brain in a continuous stream of signals, and in doing so, it creates the foundation for peace. Balance also matters in less obvious ways. Consider vision. When you turn your head to the side, your eyes remain fixed on what you are looking at. This is possible because the vestibular system signals the eyes to move in the opposite direction of the head movement, a reflex that occurs faster than thought. Without it, the world would blur and shake each time you moved. Walking would be visually chaotic, running nearly impossible. Instead, the vestibular system keeps the world visually stable, allowing you to read signs, recognize faces, and observe the environment even in motion. It is balance not only of the body but of perception itself. Children reveal to us how fundamental balance island watch a toddler learning to walk, wobbling with each uncertain step. Their vestibular system is still developing, still learning to integrate signals from muscles, joints, and vision. Each fall and each attempt strengthens that connection, until one day, without much fanfare, the child walks steadily across the room. Balance is no longer a conscious challenge but a quiet skill that frees the child to explore the world. The same process continues through games of running, climbing, skipping, and spinning. Childhood play is full of balance training, and though we think of it as recreation, it is also practice for life. At the other end of the journey, balance is what allows older adults to remain independent. As we age, the vestibular system can lose some of its sensitivity. Movements may feel less certain, walking less fluid. For this reason, balance exercises become important in later years, retraining the body to compensate. When balance is maintained, confidence grows. And with confidence comes freedom, the freedom to move, to travel. In this way, balance is not merely a sense, but a form of independence and dignity. Beyond the physical, balance carries symbolic meaning. Across cultures, to live in balance is to live in harmony. We speak of balanced meals, balanced decisions, balanced emotions. The word itself suggests steadiness, an even distribution, a state in which nothing is tipping too far one way or the other. This symbolic language reflects the same comfort that physical balance provides. Just as the vestibular system keeps the body upright, so too do we seek balance in our lives to keep our hearts and minds steady. The parallels remind us that balance is not only a function of the body, but a deeper pattern of existence. Balance also influences mood and sense of safety. When balance is disturbed, even briefly, unease follows. Dizziness can cause anxiety. Motion sickness can bring discomfort, and instability can lead to fear of falling. These reactions are not simply inconveniences, they are reminders of how central balance is to well-being. When the world feels steady, calmness is easier. When it tilts or spins, stress rises. Thus, balance serves as a bridge between body and mind, between sensation and emotion. To feel balanced is to feel secure. Animals illustrate this truth beautifully. A cat landing gracefully on its feet, a bird soaring with wings spread wide, a fish gliding effortlessly through currents. All of these creatures are living demonstrations of balance. They do not need to think about posture or stability. Their vestibular systems manage these details silently. In humans, too, athletic ability, dance, and even simple gestures of grace rely on this hidden partner. The ballet dancer spinning in pirouette, the gymnast balancing on a narrow beam, the surfer riding a moving wave. All of them are expressions of balance elevated to art, and yet the same system that supports them is the one that allows you to stand calmly in your kitchen, stirring tea without spilling. The extraordinary and the ordinary both flow from the same root. In the quiet moments of rest, balance is still present. When you close your eyes, the world does not vanish into confusion. You remain aware of up and down, of left and right, of where your body rests in space. Even in dreams, balance persists. Flying through dream skies or walking through imagined landscapes, your brain uses the sense of balance to give those experiences shape and direction. The vestibular system, always active, contributes even to the fabric of the dream world, maintaining a sense of orientation in sleep. Why balance matters, then, is not a question of luxury but of necessity. It matters because it underlies every movement, every stillness, every perception of stability. It is the silent framework upon which so much else depends. Without balance, vision falters, motion becomes difficult, rest becomes uneasy. With balance, all of these experiences flow naturally, almost invisibly, like water beneath the surface of life. As you reflect on this, you may notice a quiet gratitude for this hidden sense. Each moment of calm, each step across the floor, each breath taken in comfort is supported by balance. It is easy to forget because it is always there, reliable and constant. But by remembering it now, by bringing it gently into awareness, you may find that balance feels not only like a function of the body, but like a friend, a presence that steadies you in movement and supports you in stillness. Tonight, as you rest, balance continues its work. You are lying still, yet your inner ear is awake, confirming your orientation, stabilizing your perception, ensuring your comfort. You may not notice it consciously, but it is there, steady and tireless. Why balance matters is not a question that requires dramatic answers. It matters because it allows you to rest now, to feel secure, to let go, and to drift towards sleep with the reassurance that you are steady and safe. In this way, the vestibular system is not just an anatomical structure, but a quiet companion on your journey into rest. 3. The hidden chambers of the inner ear. Deep within the skull, beyond the outer ear that collects sound and the middle ear that amplifies it, lies the inner ear, a place of extraordinary design. This region is not large. In fact, it is compact, tucked safely within the temporal bone on each side of the head. Yet within this small space is a system of chambers and canals that serve two great purposes. One is the familiar act of hearing, translating sound waves into neural messages. The other, quieter but equally vital, is balance. It is here, in these hidden chambers, that the vestibular system resides. To understand balance, we must first picture these delicate structures, not with hurried detail but with calm imagination, as though walking slowly through a quiet gallery of anatomy. The inner ear is sometimes called the labyrinth, an ancient word that suggests winding paths and secret turns. This name is fitting, for the system is made of curved canals and rounded sacs, all filled with fluid and all shaped with precision. At first glance, it may seem like a jumble of passages, but each has a role. The labyrinth is divided into two parts, the bony labyrinth and the membranous labyrinth. The bony labyrinth is like the outer shell, carved from bone, while the membranous labyrinth lies within, a softer structure suspended inside. Between them is a space filled with fluid, known as perilymph. Inside the membranous labyrinth, another fluid flows, called endolymph. These fluids are not random. They are carefully balanced in composition and pressure, and their movement carries essential information to the sensory cells that detect motion and position. Within this labyrinth are three main components: the cochlea, the semicircular canals, and the vestibule. The cochlea is the spiral chamber associated with hearing, coiled like a snail's shell. For now, we leave hearing aside and focus on the vestibular portion, which includes the semicircular canals and the vestibule. The vestibule itself houses two important sacs called the utricle and the saccule. Together, the semicircular canals and these two sacs form the vestibular organs. They are small, so small that a person could easily overlook their significance. But they are marvels of design, each one tuned to sense a different aspect of movement. The semicircular canals are three curved tubes arranged roughly at right angles to one another. One is horizontal, one is vertical, and one is tilted backward. This arrangement allows them to detect rotation in all directions, turning the head left or right, nodding up and down, or tilting side to side. At the base of each canal is a widened area called the ampulla, and within each ampulla is a sensory structure that responds to movement of the fluid inside the canal. These canals do not respond to gravity or linear motion. Rather, they specialize in rotation. If you spin gently in a chair, it is the semicircular canals that sense it. They are like three tiny gyroscopes, each one aligned to a different plane, together forming a complete system of rotational awareness. The vestibule, meanwhile, holds the utricle and the saccule. These two sacs detect linear movements and the pull of gravity. Inside them are patches of sensory cells covered by a gelatinous layer studded with tiny crystals called otoconia. When you tilt your head, or when your body accelerates forward, backward, or upward, these crystals shift slightly under the influence of gravity or motion. Their movement bends the hair cells beneath, and the bending sends signals to the brain. In this way, the utricle and saccule tell you whether you are upright, lying down, or accelerating in a particular direction. They are your personal gravimeters, sensitive and precise, always registering how your body is aligned with the earth. Together, the semicircular canals, the utricle, and the saccule form the core of the vestibular system. Each is filled with endolymph, each lined with hair cells, and each connected to nerves that carry signals to the brain. They do not work in isolation. Rather, they form a harmonious system, overlapping in function and complementing one another. When you move, the canals and sacs respond together, sending a chorus of signals that the brain interprets as balance. The result is not confusion, but clarity. The brain integrates these signals with those from vision and proprioception, producing a unified sense of orientation. It is easy to forget how small these chambers are. The entire labyrinth could fit on the tip of a little finger, yet within it lies the foundation of balance for the whole body. Their smallness makes them vulnerable, but also makes them efficient. Nestled deep within the skull, they are protected from external harm, surrounded by bone that keeps them safe. Their fragility reminds us how remarkable it is that such tiny structures can control something as large as the posture of a human body. In a sense, the inner ear is like a hidden command center, quiet but powerful, guiding every step without ever revealing itself to consciousness. When imagining these chambers, One might picture them not as dry anatomical diagrams, but as gentle, fluid-filled arcs and sacs, like a miniature aquatic garden sealed within bone. The semicircular canals curve gracefully, looping back to meet their origins. The utricle and saccule lie nearby, modest in size, yet full of significance. All are bathed in fluid that moves softly with every tilt of the head, every shift of posture. This inner fluid world is alive with motion, though you rarely notice it. It is like a silent tide within the body, ebbing and flowing with each gesture, each nod, each step. In describing the hidden chambers of the inner ear, one might be tempted to think only in terms of mechanics, fluid, hair cells, crystals, nerves. Yet to appreciate them fully, it is helpful to consider their role in the lived experience of stability. When you stand still and feel steady, it is because these chambers confirm to your brain that you are upright. When you bend forward to tie a shoe, they inform the brain of the tilt, ensuring that muscles adjust to prevent falling. When you close your eyes, these chambers continue their work, assuring you of your position even without vision. They are the reason stillness feels like stillness, and motion feels like motion. Without them, the line between the two would blur, and the world would feel uncertain. The chambers of the inner ear have also inspired centuries of curiosity. Early anatomists, peering into the skulls of animals and humans, marveled at these winding canals and wondered at their function. Today, science explains their mechanics, yet the sense of wonder remains. How extraordinary that such small, fluid-filled structures can hold the key to balance, an ability so central to life. From the first steps of a child to the steady gait of an elder, from the slow sway of a dancer to the focused stride of a traveler, all rely on these chambers. As this part of the journey concludes, let the image of the labyrinth settle into your mind. Imagine it as a calm, hidden space, a place of curves and gentle fluid, quietly informing your brain of every posture and motion. Know that as you rest now, these chambers continue their silent work. They need no pause, no conscious command. They are always active, always attentive, always steady, and in their constancy, they provide you with the comfort of stability, the gift of orientation, and the peace of balance. 4. Semicircular canals, the arcs of motion. When we picture balance, we might think of standing upright, of walking without swaying, or of sitting comfortably without tipping over. But balance is not only about remaining still, it is also about moving smoothly through space, turning the head, tilting it to the side, spinning slowly in a circle, or even rolling over in bed. These movements all require specialized sensing. The semicircular canals, 3 curved passages deep within the inner ear, provide this ability. They are the guardians of rotational motion, silent arcs of bone and membrane that track every turn of the head, every nod, and every tilt. To imagine their function is to step into the quiet elegance of geometry and fluid, working together in perfect harmony. Each ear contains 3 semicircular canals, arranged in planes that are nearly perpendicular to one another. One is oriented horizontally, another vertically toward the front, and the third vertically toward the back. This arrangement allows them to detect movement in 3-dimensional space. Think of them as a set of 3 tiny hoops, each aligned to a different direction, so that together they can sense rotation, no matter how the head moves. When you nod yes, shake your head no, or tilt your head to one side in curiosity, one or more of these canals is at work. It is a system as simple in design as it is profound in effect. The canals are not empty. They are filled with a special fluid called endolymph, which moves in response to changes in head position, At the base of each canal is a widened chamber known as the ampulla. Within the ampulla sits a delicate structure called the cupula, a gelatinous barrier that stretches across the canal like a soft curtain. Embedded in the base of the cupula are tiny hair cells, their slender cilia extending upward into the gelatinous material. When the head turns, the inertia of the fluid causes it to lag slightly behind. This movement pushes against the cupula, bending the hair cells. The bending of these hair cells changes the signals they send to the brain, creating a precise record of motion. The semicircular canals are sensitive not to constant speed but to changes in velocity. If you begin to turn your head, the canals immediately sense the acceleration. If you stop, they register the deceleration. But if you continue spinning steadily in one direction, the fluid inside eventually catches up, and the sensation of motion fades. This explains why spinning for a long time can feel confusing. At first, you sense the movement clearly. After a while, the canals adapt. When you stop suddenly, the fluid continues to move for a moment, bending the hair cells in the opposite direction. The result is the sensation of still spinning, even though your body is at rest. This after effect is a familiar cause of dizziness, and it is a reminder of the sensitivity of the canals. Despite their small size, the semicircular canals are astonishingly precise. They can detect rotations as subtle as a fraction of a degree per second. Every tiny movement of the head is recorded and relayed instantly to the brain. The information travels along the vestibular nerve to the brainstem, where it is integrated with signals from the other ear, from the eyes, and from the body's proprioceptors. This integration allows the brain to know exactly how the head is moving, even in darkness, even when vision provides no clues. The result is smooth coordination of eye movements, muscle responses, and posture. The partnership between the semicircular canals and the eyes is especially striking. When the head turns, the canals trigger a reflex that moves the eyes in the opposite direction, keeping vision stable. This is the vestibulo-ocular reflex, and it works so quickly that it bypasses conscious thought. Without it, the world would blur each time you nodded or shook your head. Instead, your gaze remains steady, your vision clear. The semicircular canals are not only balance organs, they are guardians of stable sight. The structure of the canals has inspired comparisons to gyroscopes, those spinning devices used to maintain orientation. Like gyroscopes, the semicircular canals provide a continuous report of rotational motion. But unlike mechanical instruments, they achieve this without moving parts or spinning wheels. Instead, they rely on the physics of fluid and the sensitivity of living cells. The canals are elegant in their simplicity, relying on inertia, elasticity, and neural coding to turn motion into sensation. Children often delight in testing their semicircular canals. They spin in circles, twirl on playground equipment, or roll down grassy hills. The laughter and dizziness that follow are direct experiences of the canals at work, registering acceleration, adaptation, and after effects. With time, most of us grow less tolerant of spinning, but the fascination remains. Roller coasters, spinning rides, and even simple dance steps all play with the semicircular system, providing sensations of movement that are both thrilling and disorienting. Though these experiences can sometimes be uncomfortable, they highlight just how finely tuned our sense of rotation truly island. In daily life, the semicircular canals operate quietly, rarely announcing themselves. Turning the head to greet a friend, bending to pick up a dropped pen, rolling onto one side in bed, each of these small actions engages the canals. The brain does not need to call upon them deliberately. They are always active, always ready to detect movement and to adjust balance. Their signals flow constantly, like an invisible current guiding posture and gaze. Even in sleep, the semicircular canals remain aware. If you shift position in the night, rolling gently onto your back, the canals register the movement. They may even contribute to dreams of motion, shaping the illusions of flying, spinning, or falling that sometimes accompany slumber. The link between vestibular activity and dream sensation is subtle but real, another reminder that balance is not only physical but also part of our inner experience. Across the animal world, variations of semicircular canals are found in nearly all vertebrates. Birds have especially sensitive canals, allowing them to execute complex aerial maneuvers with precision. Fish rely on similar structures to detect rotations in water, maintaining orientation in 3 dimensions. Mammals, whether leaping, climbing, or gliding, depend on their canals to stabilize gaze and guide movement. The basic design has changed little through evolution, a sign of its effectiveness. What we carry in our skulls today is an ancient system, perfected over millions of years. To appreciate the semicircular canals is to recognize that movement is never random. Each nod, tilt, or spin is mapped instantly and faithfully by these tiny arcs. They do not ask for notice, and they do not require conscious thought. They serve quietly, guiding vision, posture, and awareness of space. As you lie in stillness now, they rest with you, but should you turn your head, they will awaken instantly, measuring the change, informing the brain, ensuring that the world remains steady. The semicircular canals remind us that life is not only about stillness but also about motion. They allow us to move through space with grace, to turn without falling, to spin without losing all sense of direction. Their quiet arcs, filled with fluid, lined with hair cells, and wired to the brain, are part of the hidden architecture of balance. They are unseen, unheard, but always working. And in their work, they provide not only stability but also the freedom to move, to explore, and to rest without fear of losing orientation. As this part draws to a close, imagine the semicircular canals as 3 gentle loops, curving in different directions, always watching over your movements. Know that they are steady, reliable, and tireless, guardians of your balance and your vision. And as you rest, they will continue their work, silent arcs of motion, keeping the world around you calm, steady, and clear. 5. The utricle and saccule, gravity's gentle guides. When we think of balance, we often imagine standing tall, holding our body steady against the pull of the earth. This quiet awareness of up and down, of lying down or standing upright, of leaning forward or stepping back, is not created by the semicircular canals alone. Instead, it comes from 2 delicate but essential structures that live within the vestibule of the inner ear. These are the utricle and the saccule, sometimes called the otolith organs, named for the tiny ear stones that help them sense position. They are not large, not even the size of a grain of rice, but their role is profound. They are the keepers of gravity, the organs that whisper to the brain where the body lies in relation to the earth. The utricle and saccule are small sacs filled with endolymph, the same special fluid that flows in the other parts of the labyrinth. Within each sac lies a patch of sensory tissue called a macula. On the surface of this macula are hair cells, the same type of sensitive receptors that appear in the semicircular canals, but arranged differently to suit their task. Above these hair cells rests a gelatinous layer, and within that layer lie minute crystals of calcium carbonate, the otoconia. These crystals are heavy compared to the fluid around them, and they shift slightly when the head tilts or when the body moves in a straight line. Their movement bends the hair cells below, and bending the hair cells creates changes in the signals they send to the brain. In this way, the utricle and saccule transform the pull of gravity and the sensation of linear motion into information the brain can use. The utricle is more sensitive to horizontal movements. When you slide forward in a chair, when you are pushed gently to the side, or when you accelerate in a car, it is the utricle that senses the change. The saccule, on the other hand, is more tuned to vertical motion. It responds when you nod your head up and down, when you rise in an elevator, or when you lie down and stand up again. Together, they provide a complete picture of how the body moves in straight lines and how it rests against gravity. Without them, the body would lose its sense of orientation. We might still know we were turning, thanks to the semicircular canals, but we would not know if we were upright or lying down, if we were moving forward or backward, upward or downward. The precision of the utricle and saccule is extraordinary. They can detect even the smallest tilts, registering angles of a degree or less. They also operate continuously, never pausing. As you sit now, or as you lie quietly in bed, they are measuring the tilt of your head, the pull of gravity on your body, and sending signals to the brain that confirm your position. These signals do not need to enter your conscious awareness. You do not have to think, "I am lying down." You simply feel secure in knowing where you are. That sense of certainty is created by these tiny sacs and the crystals they carry. It is interesting to reflect on the crystals themselves. The otoconia are simple in structure, little grains of calcium carbonate, yet they are vital to balance. Without them, the hair cells would have nothing to bend them in response to gravity. In some conditions, such as benign paroxysmal positional vertigo, these crystals can become dislodged, floating into places where they no longer belong. When that happens, sudden dizziness follows, a reminder of how such tiny structures can shape our entire experience of orientation. But when they are in their rightful place, the crystals work silently, shifting gently with each tilt and acceleration, guiding the body like grains of sand in a miniature hourglass that never stops. These organs do not work alone. The utricle and saccule send their signals along the vestibular nerve, joining the information from the semicircular canals. The brain receives this input and combines it with vision and with proprioception, the sense from muscles and joints. Together, the signals create a map of the body in space. This is why you can close your eyes and still feel whether you are upright or lying down. It is why you can ride an elevator and sense its upward or downward motion even without seeing the floors pass by. The utricle and saccule are the organs that tell you how gravity is acting on you at every moment. From the perspective of daily life, we rarely stop to notice their work. When you lower yourself onto a bed and feel the shift from vertical to horizontal, it happens smoothly. When you lean your head to one side in curiosity, or when you rest your cheek against your hand, the tilt feels natural. These sensations are made possible by the utricle and saccule. Without them, each change in position would be disorienting, leaving you uncertain of whether you were standing tall or lying flat. They are the quiet custodians of stability, ensuring that gravity, the most constant of forces, is always accounted for. In a broader sense, the utricle and saccule connect us to the earth itself. Gravity is universal, pressing gently on every living being, shaping movement and growth. Plants grow upward against its pull, animals crawl, walk, and fly within its grasp. For humans, the otolith organs are the instruments that translate this invisible force into perception. They are our constant link to the ground beneath our feet and the sky above our heads. In their signals lies the reassurance that no matter how we move, we remain oriented to the world. Across different species, variations of these organs appear, always serving the same essential role. Fish have similar structures that help them maintain position in water. Birds rely on them for stability during flight. Mammals, whether leaping, burrowing, or swimming, All depend on the information from otolith organs to stay oriented. Evolution has preserved this design for millions of years, a sign of its importance and efficiency. The utricle and saccule are ancient, yet perfectly suited to the needs of creatures living under gravity's constant influence. For humans, their importance extends even into dreams. Many people have felt the sensation of falling while asleep, a sudden jolt that startles the body awake. This is often thought to be a reflection of vestibular input, perhaps the otolith organs sending signals that the brain interprets as motion. Even in unconsciousness, the system remains active, whispering to the brain of orientation and tilt. It is always awake, always attentive, even when we are not. To think of these organs is to appreciate the harmony of small and large. Tiny crystals, delicate hair cells, microscopic sacs, all work together to create the vast sensation of steadiness in a world governed by gravity. They are unseen, unnoticed, but they are always at work. They allow you to stand, to walk, to rest, and to sleep without losing your place in space. They are the silent interpreters of the Earth's pull, transforming physics into comfort. As you rest now, you may feel the gentle weight of your body against the surface beneath you. That weight is gravity, and the knowledge of it is being carried to your brain by the utricle and saccule. They are telling you that you are lying safely, that you are still, that the world is steady. In their quiet signals lies the reassurance that you can let go, that you can close your eyes, and that you can drift into sleep without fear of losing your orientation. They are, in every sense, gravity's gentle guides, keeping you aligned with the earth and anchored in peace. 6. Vestibular hair cells, the delicate receptors. Within the labyrinth of the inner ear, inside the semicircular canals, the utricle and the saccule, lie structures so small and fragile that they are invisible to the naked eye. Yet without them, the entire sense of balance would vanish. These are the vestibular hair cells, microscopic receptors that transform motion into electrical signals, bridging the physical world of movement and gravity with the language of the nervous system. Without their presence, the flow of fluid in the canals and the shifting of crystals in the otolith organs would mean nothing. They are the translators, the interpreters, first link in the chain that connects the physics of movement to the perception of balance. A hair cell is not hair in the sense of the strands that grow from the scalp, but it is named for the fine, hair-like projections that extend from its surface. These projections are called stereocilia, and they stand in neat bundles, like rows of reeds swaying gently in a current. At the tip of each bundle lies a single, taller structure called the kinocilium, which acts as the reference point for the rest. The arrangement is precise, and the orientation of the bundle determines how the cell responds to movement. When the stereocilia bend toward the kinocilium, the cell becomes excited, increasing its rate of electrical signaling. When they bend away, the cell is inhibited, reducing its signaling. In this way, the direction of motion is encoded in the pattern of activation. The mechanism is elegant and simple. Each stereocilium is connected to its neighbor by tiny links, like threads joining one stalk to the next. When the bundle bends, these links stretch, pulling open ion channels at the tips of the cilia. Through these channels rush potassium and calcium ions from the surrounding endolymph, a fluid uniquely rich in these elements. The influx of ions changes the electrical state of the cell, leading to the release of neurotransmitters at its base. These chemical messengers cross a small gap to the afferent fibers of the vestibular nerve, triggering electrical impulses that travel to the brain. Thus, a mechanical movement, the bending of hair-like projections, is converted into the electrical signals that neurons use to communicate. Hair cells are exquisitely sensitive. Even the tiniest deflection of their cilia can alter the rate at which they fire signals. This sensitivity allows them to detect the most subtle tilts of the head, the smallest accelerations, and the faintest shifts in orientation. Yet they are also robust, capable of responding to a wide range of movements, from gentle nods to vigorous spins. Their ability to encode both direction and intensity makes them ideal receptors for balance. The brain interprets the pattern of activity across thousands of hair cells, creating a rich and continuous picture of motion and position. In the semicircular canals, the hair cells are embedded in the cupula within the ampullae. When the head rotates, the fluid lags behind, bending the cupula and the hair cells within it. In the utricle and saccule, the hair cells are located in the maculae, beneath the gelatinous layer studded with otoconia. When gravity or linear acceleration shifts the crystals, the weight bends the underlying cilia. In each case, the principle is the same. Motion bends the cilia. Bending alters electrical activity, and electrical activity becomes the signal of balance. One remarkable feature of the vestibular hair cells is their polarity. In any given patch, the orientation of the kinocilium varies, so that different cells respond to different directions of movement. In the utricle and saccule, the hair cells are arranged in a precise pattern, with a line of reversal dividing them. On one side, cells are excited by tilts in a certain direction. On the other side, by tilts in the opposite direction. This organization allows the brain to know not only that motion has occurred, but in which direction. It is a map written in microscopic bundles of cilia, a code that the brain reads effortlessly. The vestibular system, like many parts of the body, has a beautiful symmetry. Each ear contains its own set of hair cells, and together they form pairs. When the head turns to the right, hair cells in the right canal are excited, while those in the left canal are inhibited. When the head turns to the left, the pattern reverses. This push-pull arrangement ensures precision, preventing false signals and enhancing sensitivity. The brain continuously compares input from both sides, creating a balanced perception of motion. When both sides agree, the message is clear. When they disagree, such as when one side is damaged, dizziness and imbalance result. Though tiny, hair cells are living structures, subject to growth, wear, and change. They can be damaged by loud noise, by toxins, by aging, or by disease. Unlike many cells in the body, they do not regenerate easily in humans, which makes their preservation important. In some animals, however, hair cells can regenerate, restoring balance after injury. This has inspired research into whether humans might someday regain this ability, opening the door to new treatments for balance disorders. For now, the fragility of hair cells reminds us of their preciousness, of how much depends on their function. Despite their vulnerability, hair cells are remarkably enduring. For most people, they serve faithfully for decades, tirelessly converting mechanical motion into neural code. They are never silent, even at rest. A baseline level of activity flows from them constantly, allowing the brain to detect increases and decreases as meaningful changes. This continuous background makes the system responsive at all times. Even the faintest tilt of the head produces a detectable shift in activity, and the brain adjusts posture and gaze in response. In daily life, we rarely notice the work of the hair cells. When you lean back in a chair, when you nod in agreement, when you turn your head to look out a window, they are bending and firing in countless cycles. Their signals join with those of millions of other sensory receptors, creating a seamless awareness of motion and stillness. Without them, the world would spin unpredictably, and even the simplest movements would become disorienting. With them, life feels steady, grounded, and secure. It is fascinating to think that so much of our perception of space depends on structures smaller than a grain of dust. A single hair cell is measured in micrometers, yet multiplied by thousands, they give rise to the sense of balance. Their collective work allows a dancer to twirl without falling, a sailor to stand on the rocking deck of a ship, a child to swing and spin in play. They are silent collaborators in every act of motion, invisible but indispensable. As you rest now, your vestibular hair cells are quietly active. Even in stillness, they maintain a baseline of signals, confirming that the world is steady. If you shift slightly, their cilia bend, and their signals change, informing the brain of the adjustment. This happens without your awareness, without effort. It is automatic, constant, and reliable. The hair cells do not sleep. They remain vigilant, ensuring that you can rest in peace, secure in your orientation. In the grand design of the body, the vestibular hair cells are among the most delicate of instruments. They are like the strings of a finely tuned harp, vibrating with the currents of motion. Their music is not heard with the ears, but felt in the steady confidence of balance. They translate the hidden movements of fluid and crystal into the clarity of posture and gaze. In their quiet labor, they give us the gift of stability, the freedom to move without fear, and the ability to lie still and trust that the world will remain anchored. And so, as this part closes, imagine the countless microscopic bundles within your inner ear, swaying gently with each breath, each shift of position. Picture them as tiny reeds, bending in unison, whispering signals to the brain. They are delicate, yes, but they are tireless, and in their tireless work lies your calm. They are the quiet guardians of balance, the delicate receptors that transform the invisible into the real, the fragile into the steadfast. With them, gravity is no longer a mystery, motion is no longer confusing, and rest is no longer uncertain. With them, balance is possible, and peace is assured. 7. The vestibular nerve, carrying silent signals. At the heart of the vestibular system lies a remarkable partnership between tiny receptors and the pathways that carry their messages. The semicircular canals, the utricle, and the saccule are equipped with hair cells that bend with motion, releasing chemical signals to nearby nerve fibers. These fibers gather together to form the vestibular nerve, a slender but powerful highway of information. Without this nerve, the quiet movements of fluid and crystals inside the inner ear would remain local events, unshared and unrecognized by the brain. With it, they become part of the body's perception, guiding balance, orientation, and stability in every moment. The vestibular nerve is not a lone traveler. It is one branch of the vestibulocochlear nerve, also known as cranial nerve number 8. This cranial nerve has two distinct divisions, one for hearing, the cochlear nerve, and one for balance, the vestibular nerve. Side by side, these two branches emerge from the inner ear, carrying signals of sound and signals of motion toward the brainstem. Together, they form a unified line of communication, ensuring that the brain knows not only what is happening in the world of sound, but also how the body is moving through space. The duality is striking two senses, hearing and balance, intertwined at their origin, traveling together like close companions. The fibers of the vestibular nerve begin at the base of the hair cells, where neurotransmitters are released in response to the bending of stereocilia. Each hair cell connects to one or more afferent fibers, and each fiber joins many others to form bundles. These bundles then converge, forming larger trunks that come together as the vestibular nerve proper. Like a river formed by countless tiny streams, the nerve gathers small signals and channels them into a powerful flow. This flow of impulses represents the activity of thousands of hair cells, each one encoding a fragment of motion, each one contributing to the larger picture of balance. Once formed, the vestibular nerve travels through a narrow passage called the internal auditory canal, accompanied by the cochlear nerve and by facial nerve fibers. This canal is a protected corridor within the temporal bone, ensuring that the delicate fibers are shielded as they move toward the brainstem. Emerging from the canal, the vestibular nerve fibers reach their first major stop, the vestibular nuclei, located in the medulla and pons of the brainstem. Here, the signals are received, processed, and distributed further. The journey from hair cell to nucleus takes only a fraction of a second, a near instantaneous transfer that allows reflexes to be rapid and balance to be preserved in real time. The vestibular nerve is remarkable not only for its speed but also for its continuous activity. Even when the body is perfectly still, the nerve fibers are firing at a steady baseline rate. This baseline allows the brain to detect both increases and decreases in activity as meaningful changes. When the head turns to one side, the hair cells on that side increase their signaling, while those on the opposite side decrease. The vestibular nerve carries both messages simultaneously, and the brain interprets the difference. This push-pull pattern provides precision and prevents ambiguity. The nerve, therefore, is never silent. It is always carrying the silent song of balance. Whether in rest or in motion, the vestibular nerve connects not only to the vestibular nuclei but also directly to the cerebellum, a region of the brain critical for coordination and fine motor control. This direct pathway underscores the importance of balance information in movement. By sending signals straight to the cerebellum, the vestibular nerve ensures that posture and motion can be adjusted quickly and accurately. The cerebellum uses this information to fine-tune muscle activity, to correct small errors, and to make movements smooth. Without this stream of input, motion would be clumsy, posture uncertain, and reflexes delayed. What makes the vestibular nerve particularly fascinating is the variety of destinations it serves. From the vestibular nuclei, signals are sent to the spinal cord, where they influence muscle tone and posture. Other signals are sent upward to the thalamus and then to the cerebral cortex, contributing to conscious awareness of orientation. Still others are routed to the regions that control eye movements, creating the vestibulo-ocular reflex that stabilizes vision. Thus, the vestibular nerve does not carry information to a single place. Instead, it delivers its messages to multiple centers, each one using the signals in a different way. This branching ensures that balance is not a single sensation, but a coordinated system, influencing the whole body. To appreciate the importance of the vestibular nerve, one can imagine life without it. If the nerve were severed or its function disrupted, the brain would no longer receive signals of motion from one side. The result would be immediate dizziness, imbalance, and a sense of spinning. Over time, the brain can compensate by relying more on vision and proprioception, but the loss is never fully forgotten. The presence of the vestibular nerve, faithfully carrying its silent signals, is what makes steady orientation possible. It is also worth noting that the vestibular nerve is part of a bilateral system. Each ear has its own nerve, and the brain constantly compares their input. This comparison is crucial. When both sides report equally, the brain interprets stillness. When one side increases activity and the other decreases, the brain interprets motion. If the input from the two sides becomes unequal, inappropriately, because of illness, injury, or infection, the result is vertigo, the illusion of movement. The delicate balance between the two vestibular nerves mirrors the balance we feel in our bodies, a harmony that must be maintained for stability. In daily life, we do not sense the nerve itself, only the results of its messages. When you stand up quickly and feel a momentary sway, It is the vestibular nerve rushing to inform the brain of the sudden change. When you close your eyes and still know you are upright, it is the nerve carrying signals that confirm your orientation. When you turn your head and your eyes adjust instantly to keep your vision steady, it is the nerve delivering its impulses to the centers that control eye movement. Each of these small experiences is built on the constant labor of the vestibular nerve, tirelessly transmitting signals without pause. In the vast network of the nervous system, the vestibular nerve may seem modest. It is not as famous as the optic nerve that carries vision, nor as widely discussed as the auditory nerve that carries sound. Yet its work is no less vital. It is the thread that ties together the inner ear and the brain, the line along which balance becomes perception, and perception becomes stability. Its signals are silent, in the sense that they never rise to conscious awareness, but they are also indispensable. Without them, the world would feel unstable. With them, we move with confidence and rest with assurance. As you lie in quiet now, the vestibular nerve is active, carrying messages from the tiny hair cells of the inner ear to the brainstem. Each subtle shift of your head, each change in posture, alters the flow of its impulses. The brain receives them, interprets them, and adjusts the body accordingly. You may not feel this process, but you benefit from it constantly. It is a system of continuous care, a silent guardian that never ceases its work. And so, the vestibular nerve is more than a simple cable of fibers. It is a lifeline of balance, the messenger that makes orientation possible. In its steady activity lies the comfort of knowing where you are in space. In its tireless signals lies the calm of being able to rest without fear of falling. As the nerve continues its quiet transmission, you may let yourself drift deeper into relaxation, trusting that balance remains, carried faithfully by this hidden but essential pathway. 8. Brain pathways of balance. When the signals from the vestibular nerve reach the brain, they do not stop at a single destination. Instead, they spread outward, branching into many regions, each of which uses the information in its own way. The journey begins in the brainstem, a structure that sits at the base of the brain, just above the spinal cord. Here, in the medulla and pons, lie the vestibular nuclei, a cluster of neurons that serve as the primary relay station for balance. These nuclei are like a central hub in a network, receiving streams of input from the inner ears and distributing them to multiple systems throughout the body. To appreciate balance fully, we must follow the signals as they flow from this hub into the wider brain, shaping posture, eye movement, perception, and even emotion. The vestibular nuclei are divided into 4 main groups: the superior, inferior, medial, and lateral nuclei. Each has its own connections, its own responsibilities, yet they work together seamlessly. The superior and medial nuclei are heavily involved in controlling eye movements, ensuring that vision remains stable when the head moves. The lateral nucleus plays a role in sending signals down to the spinal cord, where they influence muscles and posture. The inferior nucleus integrates information from multiple senses, including vision and proprioception, blending them with vestibular input. Together, these nuclei form a sophisticated processing center, translating the raw signals from the inner ear into instructions the rest of the body can follow. One of the most immediate uses of vestibular information is the control of eye movements. The vestibulo-ocular reflex depends on rapid communication between the vestibular nuclei and the motor nuclei of the cranial nerves that move the eyes. When the head turns, the vestibular system detects the motion almost instantly, and signals are sent to the muscles that control eye position. The eyes move in the opposite direction, keeping the visual field stable. This reflex is so fast that it operates below conscious awareness. Without it, The world would blur each time the head shifted, making clear vision impossible during motion. The connection between vestibular input and eye movement is one of the clearest examples of how balance is tied to other senses, uniting movement and sight into a single, stable experience. Beyond eye control, the vestibular nuclei send powerful signals to the spinal cord through pathways known as vestibulospinal tracts. These tracts influence the tone of muscles throughout the body, especially those that maintain posture. When you sway slightly while standing, it is vestibular input that activates the necessary muscles to correct the movement and restore stability. These adjustments happen constantly, in small increments, preventing falls and maintaining equilibrium without thought. If you lean forward, muscles in your back and legs contract subtly to counteract the shift. If you tilt sideways, other muscles respond. The process is continuous, a dance of tiny corrections, guided by signals flowing from the vestibular system through the brainstem into the spinal cord. The cerebellum, a large structure located at the back of the brain, is another major partner in balance. The vestibular system sends direct input to the cerebellum, bypassing intermediate stages. The cerebellum is responsible for coordination, precision, and timing of movements. It receives vestibular information and uses it to fine-tune posture and motion, ensuring that movements are smooth rather than clumsy. For example, when walking across uneven ground, the cerebellum integrates signals of head and body position, adjusting muscle activity so that each step is stable. The cerebellum also plays a role in motor learning, meaning that repeated practice of balance-related tasks, such as riding a bicycle or learning a dance, becomes easier over time. This adaptation is made possible by the continuous partnership between vestibular input and cerebellar processing. Another destination for vestibular signals is the thalamus, a relay station deep in the brain. From the thalamus, information is sent to the cerebral cortex, where it enters conscious awareness. Here, in areas of the parietal and insular lobes, the brain creates a sense of orientation, a mental picture of where the body is in space. This is why you can close your eyes and still know that you are lying down or standing upright. The cortex integrates vestibular signals with vision and touch, producing the conscious perception of balance. Though much of vestibular processing is automatic and reflexive, this cortical involvement allows us to reflect on orientation, to describe feelings of dizziness or stability, and to make deliberate adjustments when necessary. The vestibular system also connects to regions of the brain that influence emotion and autonomic responses. Signals from the vestibular nuclei reach the hypothalamus and other centers that regulate heart rate, blood pressure, and breathing. This connection may explain why disturbances of balance, such as motion sickness, are often accompanied by nausea, sweating, and discomfort. The vestibular system is not isolated. It interacts with the body's broader regulatory networks, reminding us that balance is tied not only to movement, but also to well-being. What makes these brain pathways extraordinary is their integration. Rarely does a single region act alone. Instead, the vestibular system works by distributing signals widely, ensuring that multiple processes are informed at once. The brainstem nuclei coordinate reflexes, the spinal cord adjusts posture, the cerebellum fine-tunes movement, the cortex creates awareness, and the autonomic centers shape bodily responses. This networked approach explains why balance feels seamless. You do not sense the different contributions separately. Instead, you experience a unified state of stability. It is a harmony of systems, a concert of neural pathways that together sustain equilibrium. Disruption of these pathways illustrates their importance. If the vestibulo-ocular reflex is impaired, vision becomes unstable during motion, a condition known as oscillopsia. If the vestibulospinal tracts are affected, posture becomes uncertain, and falls are more likely. If cortical integration is disrupted, the result may be disorientation, or the perception of vertigo. Each pathway contributes to the whole, and together they create the experience of balance. The reliability of these pathways allows us to trust the world as steady, even when our bodies move within it. In daily life, these brain pathways operate so smoothly that we rarely notice them. Walking down a street, climbing a set of stairs, or turning to greet a friend all involve complex processing of vestibular signals, yet none require conscious effort. The reflexes are automatic, the corrections instantaneous, the awareness constant but unobtrusive. Only when the system is challenged, when spinning quickly, riding in turbulent motion, or experiencing illness, do we realize how much we rely on these hidden networks. Their quiet labor is what makes balance feel natural rather than extraordinary. Even in rest, these pathways remain active. As you lie down to sleep, your vestibular system continues to send signals to the brain, confirming that you are horizontal, safe, and steady. The brain receives these signals, processes them through the same nuclei and tracts, and quietly sustains your awareness of orientation. This background processing contributes to the sense of calmness, the ability to let go into sleep without fear of losing position. In dreams, too, the brain may call upon vestibular pathways, creating sensations of flying, floating, or falling. The pathways remain part of your inner world, shaping experience even when external movement is absent. The brain pathways of balance remind us that stability is not the product of a single structure, but of many working in harmony. The vestibular nuclei, the cerebellum, the spinal cord, the cortex, and the autonomic centers all share the task, each contributing a piece of the larger picture. Their integration ensures that balance is steady, that vision is clear, that posture is upright, and that orientation is certain. Without them, the world would feel uncertain, the body unanchored. With them, we move and rest with confidence. As you reflect on this, imagine the quiet web of connections inside your brain, carrying signals from the vestibular nerve to multiple destinations. Picture the nuclei as calm stations, receiving streams of information and distributing them outward, like a gentle current flowing through channels. Know that this current is always present, always guiding, always adjusting. And in that constancy lies peace, the peace of balance, carried on pathways that never rest, ensuring that you remain steady, both in motion and in stillness. 9. Working with vision. When we move through the world, we rely heavily on our eyes to tell us what is around us. We glance at the floor to see where our feet are stepping. We notice walls and doorways to guide us through a room, and we look toward the horizon to orient ourselves in space. Vision provides detail, clarity, and recognition. Yet vision on its own is fragile. If the image on the retina were to blur each time the head moved, if the eyes lagged behind when the body shifted, the world would dissolve into a dizzying haze. What prevents this blur is the constant partnership between the vestibular system and the eyes. The two senses are deeply linked, woven together in a quiet reflex that stabilizes vision whenever the head turns. This reflex is known as the vestibulo-ocular reflex, often shortened to VOR. It is one of the fastest reflexes in the human body, operating far below the level of conscious awareness. Its purpose is simple yet vital: to keep the eyes steady while the head is in motion. Imagine reading a line of text while gently nodding your head. Without the VOR, the words would jump and blur with every movement. With it, your eyes compensate instantly, moving in the opposite direction of the head turn, so that the text remains sharp and stable. This happens not through effort but automatically, triggered by signals traveling from the inner ear through the vestibular nerve into the brainstem and then out to the eye muscles. The mechanism is elegant. When the head rotates, the semicircular canals detect the motion. Their hair cells bend, sending signals through the vestibular nerve to the vestibular nuclei in the brainstem. From there, impulses are relayed to the cranial nerves that control the eye muscles. The timing is almost instantaneous, measured in milliseconds. As the head turns one way, the eyes are commanded to move the other. The amount of movement is proportional, calibrated precisely, so that the gaze remains fixed on the target. It is a balancing act between two systems, one detecting head movement and the other moving the eyes to counter it. The result is clarity in motion, a world that remains visually stable even as the body shifts. This partnership between balance and sight is easy to take for granted because it is so effective. We walk, run, or ride in vehicles, and the world appears steady. But when the system falters, its importance becomes clear. In some disorders, the VOR is weakened or lost, leading to a condition known as oscillopsia. For those affected, walking causes the world to bounce with each step. Reading becomes difficult if the head moves, and even simple tasks can become disorienting. The discomfort highlights just how much of our daily visual experience depends on the quiet cooperation of the vestibular system. The integration of vision and balance is not limited to reflexes alone. The brain also combines visual information with vestibular signals to create a sense of orientation. For example, when standing upright, the eyes see vertical lines in the environment, door frames, walls, or trees, and this visual input reinforces the vestibular sense of being aligned with gravity. If the two signals conflict, confusion arises. This is why certain illusions, such as a tilted room or a moving background, can make people feel unsteady. The vestibular system may say that the body is upright, while the eyes suggest otherwise. The brain must then resolve the conflict, sometimes creating sensations of sway or imbalance. A striking example of this interplay is motion sickness. When riding in a car, the vestibular system senses motion as the vehicle accelerates and turns. But if the eyes are fixed on a stationary object inside the car, such as a book, they send a different message: no movement. The mismatch between signals leads to discomfort, nausea, and dizziness. Conversely, looking out the window at the moving scenery often helps, because vision then aligns with vestibular input. This demonstrates the deep reliance of balance on visual confirmation and the need for harmony between the senses. Athletes and performers reveal the refinement of this partnership. A gymnast on a balance beam, a dancer spinning in pirouette, or a figure skater rotating at high speed all rely on the synchronization of vestibular and visual cues. Dancers sometimes use a technique called spotting, where the eyes fix on a single point during spins, resetting orientation and preventing disorientation. This technique demonstrates conscious use of visual input to support vestibular stability. Athletes in fast-moving sports must also coordinate these senses to keep their gaze steady on targets while the body moves dynamically. The partnership is constant, adaptable, and capable of extraordinary precision. Even in ordinary life, the link between vision and balance shapes our experiences. Walking down a hallway, lined with patterns, can create sensations of sway if the lines tilt unexpectedly. Watching a fast-moving movie scene can make some people feel as though they are moving themselves. These effects occur because the brain weights visual information heavily in constructing balance. If vision dominates, it can override vestibular signals, leading to illusions of motion. In normal conditions, the brain integrates both, trusting whichever seems most reliable. When vision and vestibular cues agree, the world feels stable. When they disagree, confusion or discomfort may follow. The importance of vision and balance is also seen when the eyes are closed. Standing still with eyes open is simple, but closing them makes the task harder. Without visual input, the brain relies more heavily on vestibular and proprioceptive signals. This is why balance tests often involve standing with eyes closed. It challenges the body to depend on inner senses. Even then, the vestibular system provides enough information to keep most people upright, though with less confidence. The absence of vision reveals just how much we depend on its constant presence to reinforce equilibrium. On a deeper level, the partnership between vision and balance reflects a larger truth about perception. No sense works in isolation. The world we experience is a synthesis, a blending of signals from multiple sources. The eyes see, the ears hear, the vestibular organs sense motion, and the muscles and joints provide proprioception. The brain does not keep these signals separate, but integrates them into a single picture of reality. Balance is not purely vestibular, and vision is not purely optical. They are part of the same network, serving the same purpose of orientation and survival. As you rest now, you can sense this partnership in its quiet form. Even though you are lying still, your eyes open or closed, the vestibular system continues to send signals of orientation. If you open your eyes, the visual confirmation of your surroundings reinforces the inner message. You are steady, safe, and at rest. If you close your eyes, the vestibular signals alone maintain this sense of stability, and the world does not vanish into uncertainty. The harmony of the two senses gives you confidence, allowing you to relax into stillness. In dreams, too, vision and balance intertwine. Flying through imagined skies or falling gently through space, the brain draws upon vestibular memories and visual imagery to create vivid sensations of movement. The partnership that sustains clarity in waking life also shapes the landscapes of the sleeping mind. It is a reminder that the vestibular and visual systems are never truly separate, even in the quiet of sleep. The collaboration of vision and balance is one of the body's most elegant designs. It ensures that the world remains stable in motion, that orientation is certain, and that life flows without disruption. It is quiet, constant, and rarely noticed, but it underlies nearly every movement and every glance. Without it, the world would blur and sway. With it, the world feels anchored and clear. As you let this thought settle, you may appreciate the silent harmony between these senses, a harmony that works tirelessly so you can move gracefully through the day and rest peacefully at night. 10. Working with proprioception. Balance is not built upon a single sense, but upon a collaboration. The vestibular system provides signals of rotation, tilt, and linear acceleration. Vision contributes information about the external world, about the alignment of lines and horizons, about movement seen around us. Yet there is another sense, one so constant that it often escapes our awareness. This is proprioception, the body's quiet knowledge of its own position. It is the awareness that your arm is bent even when your eyes are closed, the certainty that your foot rests flat against the floor without looking, the recognition of posture without deliberate thought. The partnership between proprioception and the vestibular system is fundamental, for together they weave the fabric of balance and orientation. Proprioception arises from receptors scattered throughout muscles, tendons, and joints. Specialized sensory endings respond to stretch, pressure, and movement. When a muscle lengthens, tiny fibers known as muscle spindles detect the change, sending signals to the nervous system. When a tendon is pulled, structures called Golgi tendon organs sense the tension and report it. Within joints, receptors monitor angle and movement. These signals combine to form a continuous map of body position. Even in darkness, even with eyes closed, the brain knows whether the arms are raised or lowered, whether the legs are bent or straight, whether the body leans forward or stands tall. This awareness is not conscious in the way vision island. It is a background sense, always active, always updating. The vestibular system and proprioception converge in the brainstem and cerebellum, where their signals are blended. If the vestibular system announces that the head is tilting, proprioceptive input from the neck muscles confirms or adjusts the measurement. If the vestibular system indicates that the body is swaying, proprioceptive signals from the legs and feet provide detailed feedback about pressure shifting across the soles. This integration creates stability. Each system alone offers valuable information, but together they provide a more reliable account of the body's orientation. The brain compares their messages, checks them against vision, and produces a unified sense of balance. The importance of proprioception becomes clear when standing on an uneven surface. Imagine walking barefoot along a sandy beach. With each step, grains of sand shift beneath the foot. Proprioceptors in the muscles of the ankle and foot register these changes, reporting the tilt and pressure of each movement. The vestibular system, meanwhile, senses the overall orientation of the head and body relative to gravity. Working together, they allow you to remain upright, adjusting posture moment by moment. The brain does not issue commands blindly, but relies on this dual input to maintain equilibrium. Without proprioception, each step on shifting ground would feel uncertain. Without vestibular input, the ground might feel stable, but the sense of verticality would be lost. Together, they make walking across sand possible and even effortless. Another example can be seen when standing still with eyes closed. Vision is removed, leaving vestibular and proprioceptive senses to sustain balance. The vestibular system reports the body's orientation to gravity, while proprioceptors in the legs and core muscles signal every small sway. The brain uses this information to activate muscles that restore equilibrium. Even when apparently motionless, the body is never completely still. It sways gently, like a tree in the wind, corrected continuously by reflexes. These corrections depend on the quiet cooperation of vestibular and proprioceptive input. If one is weakened, the other compensates, but the effort is greater and the stability less certain. Athletes often demonstrate the refinement of this partnership: a gymnast balancing on a narrow beam, a surfer riding a moving wave, or a tightrope walker stepping across a rope, all depend on constant feedback from both vestibular and proprioceptive systems. The vestibular system signals overall orientation, while proprioceptors in the feet, ankles, and core muscles provide precise adjustments. Training strengthens the ability to integrate these signals, leading to remarkable feats of balance that seem effortless to the observer. Yet beneath the surface, countless signals are being processed each second, guiding muscles with exquisite timing. The connection between proprioception and vestibular input also plays a role in rehabilitation. When someone loses part of vestibular function, exercises are often prescribed that emphasize body awareness. Patients may be asked to stand on foam surfaces, to move their head while walking, or to practice balancing with eyes closed. These exercises strengthen proprioceptive feedback, helping the brain adapt to the loss by relying more heavily on other senses. The plasticity of the nervous system allows it to reweight inputs, to depend more on proprioception when vestibular signals are unreliable. This adaptability demonstrates the resilience of balance as a system built not on a single source but on integration. Interestingly, proprioception and the vestibular system sometimes come into conflict. Imagine standing on a boat that rises and falls with the waves. Proprioceptors in the legs and feet report that the body is swaying, while the vestibular system also detects motion relative to gravity. But if the eyes focus on the unmoving interior of the cabin, vision sends a different message. The body is still. The mismatch between these senses creates discomfort, sometimes nausea. In this case, the vestibular and proprioceptive senses agree with one another. While vision disagrees, the brain must resolve the conflict, and the result can be motion sickness. This example shows how tightly interwoven these senses are and how discord between them can unsettle the entire system. Children, as they grow, gradually develop the integration of vestibular and proprioceptive senses. When infants first begin to stand, their balance is unsteady. They topple easily, for the coordination between inner ear signals and body awareness is still developing. Through repeated attempts, through play, crawling, walking, and climbing, the senses learn to cooperate. The child becomes more stable, able to stand confidently and walk with ease. Playgrounds provide natural challenges to these systems, encouraging children to climb, swing, and balance, strengthening the integration that will serve them throughout life. At the other end of life, aging can reduce both vestibular sensitivity and proprioceptive acuity. Muscles may weaken, joints may stiffen, and inner ear structures may lose some function. The combination can lead to unsteadiness or falls. Yet awareness of this decline has led to practices that preserve balance in older adults. Tai Chi, yoga, and balance exercises emphasize slow, deliberate movements that engage both vestibular and proprioceptive senses. By strengthening awareness of posture and motion, these practices help maintain stability and confidence. The lesson is clear. Balance can be nurtured by training both the inner ear and the body's sense of itself. As with vision, proprioception also plays a role in dreams and the imagination of movement. When dreaming of running or flying, the brain calls upon stored patterns of vestibular and proprioceptive activity, simulating the sensations of motion. Even when still, the nervous system can conjure the experience of movement by recreating the interplay of these senses. This shows how deeply balance is embedded in our perception of reality, not only shaping waking action, but also coloring the landscapes of the mind. In the quiet moments of rest, proprioception and vestibular input continue to work. As you lie still, the vestibular system confirms your horizontal orientation, while proprioceptors in muscles and joints signal that your body is relaxed, that weight is evenly supported. Together, they provide assurance that you are safe and steady. This partnership allows you to release tension, to let go of conscious control, and to drift toward sleep. Even without awareness, the senses remain active, guardians of stability. The collaboration between vestibular input and proprioception demonstrates the wisdom of redundancy in nature. No single sense carries the entire burden of balance. Instead, multiple systems share the task, reinforcing one another, compensating when one is weakened. This design provides resilience, ensuring that even in challenging conditions, stability is possible. It also provides flexibility, allowing humans to walk on solid ground, balance on moving surfaces, and adapt to countless environments. As this part of the journey closes, imagine the quiet dialogue between your inner ear and your body. The vestibular system whispers of gravity and motion, while proprioceptors respond with details of muscle stretch and joint position. Together, they form a conversation that never stops, a background harmony that steadies you in every posture and every movement. They are silent companions, unnoticed but essential, shaping the grace of walking, the calm of standing, and the peace of lying down. In their partnership lies the true foundation of balance, not a single voice but a chorus, guiding you always toward stability and rest. 11. Every day. Balance in action. Balance is often thought of in abstract terms, as something to study in anatomy or physiology. But in truth, it is lived every moment of the day. Each movement, each stillness, each transition from one posture to another is shaped by the continuous work of the vestibular system, vision, and proprioception. Though invisible, this system is not theoretical. It is what allows you to rise from bed in the morning, walk across a room, reach for an object, or lie down again at night. To appreciate its importance, it is useful to look at ordinary life and see how balance weaves through its fabric, not as something unusual, but as something always present, always guiding. Consider the simple act of standing. On the surface, it appears effortless. You plant your feet, straighten your back, and remain upright. Yet beneath the surface, thousands of adjustments take place each second. Muscles in your legs, back, and abdomen contract and relax in subtle patterns. Proprioceptors in your joints report small sways. Vestibular signals track head position, and vision provides reference points in the environment. The brain blends this information and sends corrective signals to keep you from toppling. The stillness you feel is an illusion, for the body is never perfectly still. It sways in quiet arcs, continuously corrected by reflexes so small and fast that they escape awareness. Standing upright is not a state of immobility, but a dynamic balance, maintained through constant feedback. Walking extends this principle. Each step requires a controlled fall forward, the body leaning, the foot swinging, and the other leg catching the weight. Balance guides each phase. As the head shifts slightly, vestibular input signals the motion. Proprioceptors in the ankles and knees update the brain on joint position. Vision confirms the path ahead. The integration of these senses creates fluid motion. Without balance, walking would become unsteady, uncertain, and effortful. With it, the steps flow naturally, allowing attention to turn elsewhere toward conversation, scenery, or thought. Walking feels simple, but in truth it is an orchestration of balance, carried out seamlessly and without conscious effort. Even sitting engages balance. When you lower yourself into a chair, the vestibular system registers the downward motion. Proprioceptors signal joint angles changing, and muscles coordinate to control the descent. Once seated, the body adjusts posture to remain upright. Subtle contractions, preventing slumping or tipping. If you shift in the chair, leaning to one side or reaching for an object, balance accommodates the movement instantly. We rarely think of sitting as a balancing act, yet it too depends on continuous adjustments. The comfort of rest in a chair is possible because the body knows where it is in space, anchored by balance signals. Reaching for an object illustrates another layer of this quiet system. Imagine extending your arm to pick up a glass of water from a table. As you reach, your body shifts slightly, weight distributing differently across the feet. The vestibular system detects the tilt, proprioceptors signal muscle stretch, and reflexes adjust posture to prevent loss of balance. You may not notice these corrections, but they are happening with each motion. Even lifting the glass requires subtle coordination, as its weight alters the balance of your body. The brain accounts for this instantly, engaging muscles to maintain stability. Such tasks feel routine because balance makes them so, weaving stability into every action. Balance is also at play when we change positions, such as moving from sitting to standing or from standing to lying down. Rising from a chair requires shifting weight forward, pushing through the legs, and straightening the body. Each stage engages vestibular input, proprioceptive feedback, and muscular coordination. Without balance, the motion would be clumsy, perhaps even dangerous. With balance, it becomes smooth. Similarly, lying down is more than collapsing onto a surface. The body must control the descent, orient itself relative to gravity, and adjust posture once horizontal. Vestibular signals confirm the change. Proprioception tracks limb positions, and the brain orchestrates the process. The ease with which we lie down is a testament to balance in action. Children learning to walk reveal the hidden labor of balance most clearly. At first, their steps are tentative, their gait unsteady. Falls are frequent, for the integration of senses is still maturing. Yet with practice, balance develops, and the steps become more confident. Soon the child walks without thought, runs with joy, and climbs with daring. What was once uncertain becomes automatic. Adults may forget the effort once required, but every stride still depends on the same system. Balance is not a skill outgrown. It is one sustained throughout life, present in each motion, no matter how small. Play and recreation often highlight balance more vividly. Riding a bicycle, skating on ice, or climbing a tree all test the system in new ways. The vestibular organs detect tilts and rotations. Proprioceptors provide feedback from muscles under strain, and vision offers external reference points. The brain blends these signals to maintain equilibrium even in challenging conditions. A cyclist leaning into a curve, a skater gliding smoothly across ice, or a child balancing on a low wall, all are demonstrations of balance extended beyond the ordinary. They remind us that balance is not only about safety but also about freedom. The freedom to explore new movements and environments, even moments of stillness. Closing the eyes in meditation, engage balance. With vision removed, the brain relies more heavily on vestibular and proprioceptive input. The awareness of uprightness, of head aligned over shoulders, of feet grounded, is sustained by these senses. The quiet calm of stillness is built upon their constant work. The ability to let go into relaxation depends on the assurance that the body is stable. Thus, even the act of resting in stillness is an expression of balance, as essential as walking or standing. At night, balance continues to serve in subtle ways. Rolling in bed, turning onto one side, or shifting the head on the pillow, all engage vestibular signals. The brain adjusts posture unconsciously, preventing disorientation. Even dreams sometimes echo the sensations of balance, falling, flying, floating, drawing upon vestibular memories. The sense of orientation never fully sleeps. It remains active, ensuring that rest is safe and steady. Balance in action does not cease with consciousness. It persists through every phase of being. The everyday role of balance is most evident when it is disturbed. A brief spell of dizziness, a sudden loss of equilibrium, or the unsteady feeling after spinning in circles quickly reveals how much we rely on balance. Tasks that once felt effortless become difficult. Standing, walking, or even sitting feels insecure. Such moments highlight the hidden labor normally performed without recognition. Balance is not a luxury. It is a necessity, the background condition that makes daily life possible. And yet, for most of the time, balance is invisible. We do not marvel at the ease of walking across a room, or at the stability of sitting in a chair. We do not notice the adjustments that prevent falls, or the reflexes that steady vision. Balance works silently, asking for no attention, providing its service without fanfare. It is a constant companion, steadying life from the smallest gesture to the largest stride. As you reflect on these everyday examples, you may feel gratitude for this quiet system. Each moment of stability, each smooth transition, each comfortable rest is a gift of balance. It is there in the background, unheralded, yet essential. In every action, balance is at work, weaving stability into the fabric of life. As you lie still now, the same system continues to serve, keeping your orientation clear, your posture secure, your body at peace. Everyday balance in action is not only the foundation of movement, but also the foundation of calm, allowing you to trust the world as steady and to surrender gently to rest. 12. Motion and dizziness. Among the many sensations the body can create, Few are as striking or as memorable as dizziness. It is a feeling that can arrive suddenly, a spinning of the world, a tilt beneath the feet, a wave of imbalance that makes even stillness feel uncertain. To some it is unsettling, to others it is curious, but to all it is a reminder of the delicate nature of balance. Dizziness, seasickness, and motion sickness are not flaws in the vestibular system, but natural consequences of how it works, signals that the inner ear, the eyes, and the body are sending mismatched messages. By exploring these experiences gently, without alarm, we can see how they arise and how they reflect the normally seamless operation of the vestibular system. When the head turns, the semicircular canals detect rotation by the movement of fluid within them. Normally, this fluid movement is brief and proportional, creating accurate signals. But when spinning continues, as when a child twirls in circles or when someone rides a rotating amusement park ride, the fluid catches up with the movement, and the hair cells within the ampullae return to baseline. The sense of rotation fades, even though spinning continues. Then, when the body stops, the fluid keeps moving for a moment longer, bending the hair cells in the opposite direction. The result is the sensation of spinning, even though the body is still. This after effect, familiar to anyone who has spun around quickly, is one form of dizziness. It illustrates the sensitivity of the semicircular canals and their reliance on changes in motion rather than constant speed. Another form of dizziness arises when the utricle or saccule, the gravity-sensing organs of the vestibular system, encounter dislodged crystals. Normally, the tiny otoconia rest upon the gelatinous layer above the hair cells, shifting gently with gravity and linear acceleration. But in some people, these crystals can become dislodged and drift into the semicircular canals. When this happens, even small head movements can cause abnormal stimulation of the hair cells, creating brief but intense vertigo. This condition, known as benign paroxysmal positional vertigo, is common and usually harmless, but it demonstrates how even tiny changes within the inner ear can alter the perception of motion. Motion sickness, a more widespread experience, is rooted in the conflict between the vestibular system and vision. Imagine sitting inside a car, reading a book, while the vehicle moves along a winding road. The vestibular system senses the motion, the turns, the accelerations, the shifts of direction. But the eyes, fixed on the unmoving page, tell the brain that the body is still. The conflict between these two sources of information creates confusion in the nervous system, leading to discomfort, nausea, and dizziness. Looking out the window, however, usually helps, for vision then aligns with vestibular input. The scenery passes by, confirming the sense of motion, and the conflict eases. The reverse can also occur, as in certain virtual reality experiences. Here the eyes see motion, the visual field moves and tilts, as though the body were traveling through space, yet the vestibular system reports stillness. The brain again receives conflicting messages, and the result can be dizziness or nausea. These examples show that balance depends not only on the accuracy of individual senses, but on their agreement. When vision, vestibular input, and proprioception all align, the experience is smooth and comfortable. When they disagree, disorientation arises. Even ordinary life provides small examples of dizziness. Rising too quickly from a lying position may cause a brief rush of unsteadiness. Though often linked to blood pressure changes, the vestibular system is involved as well, adjusting rapidly to the new orientation. Similarly, closing the eyes while spinning in circles makes dizziness more pronounced, because vision is no longer available to stabilize the sensation. These moments, though temporary, remind us of the dependence of balance on multiple senses working together. Astronauts in space offer another perspective. In the absence of gravity, The utricle and saccule lose their usual frame of reference. The otoconia no longer shift in a meaningful way, and the brain receives unusual signals. At the same time, vision continues to provide cues, but these may conflict with vestibular input. The result, especially in the first days of spaceflight, is often motion sickness, known as space adaptation syndrome. With time, the brain adjusts, learning to reinterpret signals in the absence of gravity. This adaptability demonstrates the flexibility of the vestibular system, its ability to recalibrate when familiar conditions change. While dizziness may seem uncomfortable, it is worth remembering that it is simply the brain's response to unexpected or mismatched signals. It is not a threat in itself, but a message that the senses are out of alignment. In fact, the variability to feel dizziness is evidence of the vestibular system's sensitivity. If the system were less precise, if it ignored mismatches, we might lose the ability to detect disorientation. By creating the sensation of dizziness, the body encourages caution, reminding us to stop, to steady ourselves, to wait until balance is restored. There is also a curious connection between dizziness and emotion. Many people describe dizziness as disorienting not only physically but also psychologically. The loss of stability can create feelings of anxiety or unease. This link is partly biological, for the vestibular system connects with regions of the brain that regulate emotion and autonomic responses. It is also symbolic, for balance is associated with security, while imbalance suggests vulnerability. Yet just as quickly as dizziness arrives, it often fades, leaving behind a renewed appreciation for the constancy of balance when it is working smoothly. Children often play with dizziness deliberately, spinning in circles until they collapse with laughter. They enjoy the temporary disorientation, the strange sensation of the world tilting. This playful use of dizziness demonstrates its harmlessness in small doses, and its role in training the brain to recover from imbalance. The joy of spinning fades with age, but the memory of it remains. A reminder of how adaptable and resilient the vestibular system island. In adulthood, dizziness may come less from play and more from fatigue, illness, or imbalance of the senses. Yet even here, the body's capacity to recover is strong. With time, with stillness, with the reassertion of agreement between vision, vestibular input, and proprioception, stability returns. The brain learns to trust the senses again, and calm follows. This recovery shows that dizziness, though disruptive, is usually transient, a brief interruption in the otherwise seamless flow of balance. As you lie and rest now, it may be comforting to know that dizziness is the exception, not the rule. The vestibular system, vision, and proprioception are usually in harmony, guiding you smoothly through life without notice. Dizziness only occurs when this harmony is disrupted, and even then it is a temporary signal, a reminder of the system's precision. The constancy of balance is far greater than its rare interruptions, and so, motion and dizziness are not signs of failure, but demonstrations of how finely tuned the system island. They reveal the reliance of balance on multiple senses and the importance of their agreement. They remind us that stability is a product of cooperation, of signals converging and aligning, and they highlight the adaptability of the brain, its ability to recalibrate when conditions change. As unsettling as dizziness may feel, it is also a testament to the remarkable sensitivity of the vestibular system, a sensitivity that serves us well in every moment of balance. As this part concludes, imagine the harmony of your senses working together now. The vestibular system whispers of stillness. Proprioceptors confirm the weight of your body against the surface, and vision, if your eyes are open, aligns with these signals. There is no conflict, no mismatch. The world feels steady, the body feels secure, and the mind can let go. In this harmony lies peace, a peace that carries you gently towards sleep, steady and calm, unshaken by the passing possibility of dizziness, anchored always by the strength of balance. 13. Balance across the lifespan. Balance is not a fixed ability, granted all at once, but a sense that changes with time, shaped by growth, experience, and aging. From the earliest days of life in the womb to the final years of old age, the vestibular system develops, adapts, and sometimes declines. It is a companion through every stage, guiding first steps, supporting graceful movement in youth, and later requiring care and attention to maintain stability. To see balance across the lifespan is to see not only the biology of the vestibular system, but also the story of human life itself, woven through with the themes of growth, adaptation, and continuity. Even before birth, the vestibular system is among the first senses to develop. In the womb, as the mother moves, the fluid-filled canals and otolith organs of the fetus respond. The rocking and swaying of the maternal body become the fetus's earliest lessons in motion, long before eyes open to the outside world. The inner ear is already learning to interpret movement. This may explain why gentle rocking is so soothing for newborns. It echoes the rhythms of life before birth, when vestibular signals were constant companions in the dark and fluid environment of the womb. The sense of balance is, in this way, one of our oldest senses, grounding us even before our first breath. In infancy, balance begins as a fragile, developing ability. Newborns cannot yet control their posture. Their heads wobble, their limbs move without coordination. But with time, the vestibular system, proprioception, and vision begin to integrate. By 3 to 4 months, infants can lift their heads steadily when lying on their stomachs. By 6 months, many can sit without support, a milestone of balance as much as strength. Each wobble and topple is part of the learning process, the brain calibrating vestibular signals against muscle activity and visual feedback. The great triumph of balance in early childhood is walking. Around the end of the first year, the toddler takes hesitant steps, arms outstretched for stability, feet wide apart. Falls are frequent, but each attempt strengthens the coordination between vestibular input, proprioception, and vision. Over weeks and months, the gait becomes steadier, the steps more confident. Running soon follows, then climbing, then jumping. Balance is not perfected all at once, but built gradually through repeated challenges and corrections. Childhood play, swinging, spinning, balancing on beams further develops the system, teaching the brain to handle complex motions and recover quickly from imbalance. By the school years, balance has become reliable enough to support more intricate movements. Children can ride bicycles, skate, and participate in sports that require quick changes of direction. The vestibular system is now well integrated with vision and proprioception, allowing fluid coordination. Still, children often test the limits of their balance, spinning in circles or hanging upside down, exploring sensations of dizziness, as if to learn their own boundaries. These playful experiments strengthen their adaptability, preparing the system for the challenges of adult life. In adolescence, balance reaches a new peak. Growth spurts may temporarily disrupt coordination, as the brain recalibrates to longer limbs and shifting centers of gravity. But once adjusted, the capacity for balance expands. Dancers, athletes, and performers refine their abilities through training, pushing the vestibular system to its limits. The spins of figure skating, the flips of gymnastics, the footwork of martial arts, all are made possible by the integration of vestibular, visual, and proprioceptive input. At this stage of life, balance is not only about stability, but about agility, precision, and grace. It becomes an expression of artistry as well as biology. Adulthood generally brings stability and balance. By the 20s and 30s, the vestibular system is mature, and coordination is at its most reliable. Daily activities are carried out smoothly, with little awareness of the system at work. Most adults can trust their balance without thought, whether walking across a crowded street, carrying heavy objects, or navigating uneven terrain. Yet even in this period of stability, the vestibular system is active every moment, maintaining equilibrium in countless subtle ways. Its constancy is so complete that it vanishes from awareness, taken for granted as part of the background of life. As the years advance into middle age, small changes may begin to appear. Reflexes can slow slightly, and recovery from dizziness may take longer. These changes are usually subtle, unnoticed in daily life, yet they remind us that balance, like all systems, is not immune to time. The resilience of the vestibular system carries most people through middle adulthood without difficulty, but the groundwork is being laid for later changes. Exercise, activity, and practice during these years help preserve balance, strengthening muscles, and maintaining coordination. In older age, balance becomes more fragile. The hair cells in the vestibular organs may decline in number, reducing sensitivity. The nerve fibers carrying signals to the brain may transmit less efficiently. At the same time, vision may weaken, and proprioception may be dulled by changes in joints and muscles. Together, these shifts can lead to unsteadiness, slower reflexes, and increased risk of falls. For many older adults, balance becomes a conscious concern, rather than an unnoticed background function. Walking on uneven surfaces, climbing stairs, or even rising from a chair may require more attention than before. Yet, balance in old age is not simply a story of decline. The nervous system retains a remarkable capacity to adapt. With practice, older adults can strengthen proprioceptive awareness, improve posture, and train the brain to rely more on vision. Gentle exercises like Tai Chi and yoga emphasize slow, deliberate movements that challenge balance in safe ways, keeping the system engaged. Even walking regularly helps preserve stability, encouraging the integration of vestibular, visual, and proprioceptive input. In this way, balance can be nurtured and extended, supporting independence and well-being well into later years. Balance across the lifespan also carries symbolic meaning. In infancy, balance represents growth and discovery, the first steps into the world. In youth, it represents mastery and expression, the joy of movement refined into skill. In adulthood, it represents confidence, the ability to move through life with assurance. In old age, it represents resilience, the effort to maintain stability against the pull of time. At every stage, balance is both physical and metaphorical, a mirror of the challenges and strengths of life itself. It is worth remembering that balance is never absent, even when challenged. The vestibular system may weaken, but the brain finds ways to adapt. Vision may fade, but proprioception can grow stronger. Falls may occur, but recovery is possible. Balance is not a single ability to be gained or lost, but a dynamic interplay of systems, always changing, always capable of adjustment. This adaptability is what allows humans to live long lives filled with movement, to grow from the wobbling steps of infancy to the careful strides of old age. As you rest now, reflect on your own journey of balance. Recall the first steps of childhood, the playful spins, the confident strides of youth, the calm stability of adulthood, and the adaptations of later years. Each stage has been guided by the vestibular system, always active, always present. It is a sense that has walked with you through every moment, from your earliest days to now. and in its constancy lies comfort, the reassurance that balance has always been with you and will continue to steady you through every stage of life. 14. Balance in other animals. The vestibular system is not unique to humans. It is an ancient design, one that has been preserved and refined over millions of years of evolution. Across the animal kingdom, from the smallest fish in the ocean to the largest birds in the sky, creatures rely on balance to navigate their environments. Though the forms and specializations vary, the basic principle remains the same: the detection of motion, orientation, and gravity through fluid-filled chambers and sensitive receptors. To explore balance in other animals is to glimpse the diversity of life shaped by a shared need for stability in a world where movement is constant. The origins of the vestibular system can be traced far back to fish. Among the earliest vertebrates, fish live in an environment where three-dimensional movement is the rule, not the exception. They swim upward and downward, forward and backward, turning with precision in the water. To manage this complexity, they rely on otolith organs, similar to those found in humans. These organs detect gravity and linear acceleration, allowing fish to sense their orientation in the water. In addition, many fish possess lateral line systems, sensory structures that detect water currents and vibrations. Together, these systems allow them to glide, hover, and dart with remarkable control. The evolutionary blueprint of balance was established in these aquatic ancestors, a foundation upon which later species would build. Amphibians and reptiles, stepping onto land, adapted the vestibular system to new challenges. Frogs, for instance, must coordinate jumps and landings, leaping through the air with arcs of motion that require precise orientation. Their vestibular organs help them judge trajectory and maintain posture mid-leap, ensuring they land successfully. Lizards, skittering across uneven terrain, depend on rapid vestibular reflexes to stabilize vision while darting from predator to shelter. Even turtles, moving more slowly, rely on balance to navigate both land and water, adjusting posture as they transition between environments. Birds demonstrate some of the most sophisticated vestibular adaptations in nature. Flight demands exquisite control of orientation. A bird in the air must adjust constantly to shifting winds, tilts, and rotations. The semicircular canals of birds are often larger relative to body size than those of mammals, reflecting their importance in detecting rapid head movements. A falcon diving at high speed, a swallow weaving through the air, or an owl turning its head nearly all the way around, all rely on vestibular precision. The integration of vestibular input with vision is especially critical in birds, whose survival depends on accurate targeting of prey or navigation across vast distances. Migratory birds, traveling thousands of miles, not only use celestial cues and magnetic fields but also rely on their vestibular systems to stabilize flight and coordinate orientation across long journeys. Mammals, too, show the versatility of balance. Cats are among the most celebrated examples, famed for their ability to land on their feet. This so-called righting reflex depends heavily on vestibular input. When a cat falls, its inner ear quickly detects orientation in space, and the body twists to align feet downward. The precision of this response, often occurring in fractions of a second, highlights the sensitivity of the vestibular system. It is not magic, but biology, refined through evolution for survival. Other mammals demonstrate different adaptations. Bats, navigating in the dark through echolocation, also rely on vestibular cues to stabilize flight. Their semicircular canals, though small, are tuned to their rapid wing beats and agile maneuvers. Aquatic mammals such as dolphins and seals must manage balance in both water and air. Their vestibular systems are adapted for swimming, with some differences in size and shape compared to land mammals. Yet the fundamental design remains the same. Canals, otolith organs, and hair cells translating motion into signals for the brain. Even in animals not often associated with agility, balance is essential. Grazing animals such as horses, cows, and deer rely on steady posture to feed safely, while keeping alert to their surroundings. The vestibular system ensures that even as they lower their heads to graze, they remain oriented and ready to respond to threats. Primates, including humans, have vestibular systems adapted for climbing, leaping, and moving through trees. The challenges of arboreal life demand constant balance, integrating vestibular, visual, and proprioceptive signals to navigate branches with accuracy. Insects, though lacking the vertebrate vestibular system, have evolved their own balance organs. Flies and mosquitoes, for example, possess structures called halteres, small knob-like organs that act as gyroscopes. As the insect flies, the halteres vibrate, detecting body rotation and helping stabilize flight. Though structurally different from semicircular canals, halteres serve a similar function, highlighting how the need for balance drives diverse evolutionary solutions. Other invertebrates use different strategies. Crustaceans, such as lobsters and crabs, possess statocysts, small balance organs containing grains of sand or mineral particles that shift with motion. These organs provide information about orientation, much like otoliths in vertebrates. The variety of balance adaptations across the animal kingdom underscores its importance for survival. Whether flying, swimming, crawling, or walking, animals must maintain orientation to interact with their environments effectively. Balance enables predators to hunt and prey to escape, birds to migrate, fish to school, and mammals to care for their young. It is not an optional feature, but a universal necessity. The vestibular system, or its equivalents, is one of the great unifying features of life. Studying balance in animals also deepens our understanding of humans. The similarities remind us that our own vestibular system is part of an ancient lineage, shaped by the same forces that shaped fish, birds, and mammals. The differences reveal how flexible this sense can be, adapting to the demands of each environment. By observing cats landing on their feet, we learn about reflexes. By watching birds stabilize their gaze in flight, we see the integration of vision and vestibular signals. By examining fish swimming in 3 dimensions, we appreciate the origins of balance itself. Each species teaches us something new, yet all return to the same principle: the detection of motion and gravity through specialized organs. Beyond survival, balance contributes to the beauty of animal life. The soaring of an eagle, the leaping of a gazelle, the diving of a dolphin, all are expressions of grace, made possible by vestibular function. Balance is not only functional but aesthetic, shaping movements that inspire awe. Even the simplest acts, such as a kitten playfully tumbling and regaining its footing, remind us of the elegance hidden within the vestibular system. It is a sense that does not draw attention to itself, but allows life to unfold with fluidity and rhythm. As you reflect on balance in other animals, imagine the diversity of creatures across the earth, each guided by its own version of this sense. Picture the fish gliding through water, the bird wheeling through the sky, the cat twisting mid-air, the insect buzzing with halteres vibrating. Each movement is steady, each posture assured, each life supported by the quiet power of balance. And in recognizing this, you may feel a connection, a kinship across species, for the same sense that steadies them, steadies you as well. Balance is a thread running through the fabric of life, binding together the great variety of living forms in a shared rhythm of stability. As this part closes, let this thought bring calm. Balance is universal. It is not limited to humans, but shared across creatures of land, sea, and sky. It is an ancient inheritance, a common gift of life, always present, always steadying. In knowing this, you may feel yourself part of something vast and enduring, a living world held together by the quiet constancy of balance. 15. The vestibular system in space. On Earth, balance is built upon a foundation so constant that we rarely give it thought. The pull of gravity, every tilt of the head, every step, every lean, is measured against this invisible force. The utricle and saccule rely on it, their tiny crystals shifting in response to gravity's downward pull. The semicircular canals measure motion relative to it, always aware of what is up and what is down. But in the environment of space, gravity as we know it disappears. Astronauts floating in orbit find themselves in microgravity, where objects drift and orientation is no longer defined by weight. In this altered world, the vestibular system faces a challenge unlike any it encounters on Earth. Its signals must be reinterpreted, its functions recalibrated, and its meaning reconsidered. Exploring how the vestibular system adapts in space reveals both the fragility and the resilience of balance. In the first days of spaceflight, astronauts often experience what is called space motion sickness. The symptoms are familiar: nausea, dizziness, disorientation, and fatigue. They arise not from illness, but from sensory conflict. On Earth, the otolith organs, the utricle and saccule, use gravity to determine head orientation. When the head tilts, the otoconia shift, bending the hair cells and signaling the change. But in microgravity, the otoconia no longer settle downward. Instead, they drift with the head, failing to provide consistent signals. The brain, accustomed to interpreting their messages as indicators of tilt, receives confusing information. At the same time, vision reports that the body is floating and rotating freely, often without the usual visual anchors of up and down. The result is conflict between vestibular and visual inputs, producing discomfort. The semicircular canals, which detect rotational acceleration, continue to function in space, but without gravity, they too face challenges. Normally, after rotation stops, gravity helps the fluid settle back into place. In space, the fluid continues drifting longer, causing prolonged or distorted signals. This contributes to illusions of motion, where astronauts feel as though they are spinning or tilting, even when they are not. Such illusions can be disorienting, particularly in the confined, equipment-filled environments of spacecraft, where accurate orientation is essential. Yet the brain is remarkably adaptable. The brain learns to reinterpret vestibular signals, relying more on vision and proprioception to determine orientation. Floating becomes natural, and tasks are carried out smoothly. What was once disorienting becomes routine. This adaptation reflects the flexibility of the nervous system, its ability to recalibrate when conditions change. The vestibular system does not fail in space. Rather, the brain learns to use it differently. Life aboard spacecraft provides unique examples of this adaptation. Astronauts quickly develop a new sense of up and down, defined not by gravity, but by habit and visual cues. For instance, in a space station, the floor may be defined as the surface where equipment is mounted, even though all directions are physically equivalent. When multiple astronauts float in the same module, they may each orient themselves differently, one upside down relative to another, without discomfort. This shows how orientation becomes relative, shaped more by visual context than by vestibular input. The brain's reliance on vision grows, while vestibular signals recede in importance. Despite adaptation, challenges remain. Returning to Earth after extended spaceflight often brings a period of readjustment. Astronauts may feel unsteady, as though the ground is shifting beneath them. The otolith organs, long unused to gravity, must recalibrate, and muscles weakened by weightlessness must relearn the constant effort of standing upright. Some astronauts describe walking as difficult, their steps hesitant, their posture uncertain. With time, the system readapts and balance returns. This cycle adaptation to microgravity and readaptation to Earth illustrates the plasticity of the vestibular system, but also its deep reliance on gravity as a reference. The study of balance in space has broader implications. It teaches us that the vestibular system, though finely tuned to Earth's environment, is not fixed. It can adjust to new conditions, relying on other senses when gravity is absent. It also reveals the close integration of vestibular, visual, and proprioceptive inputs, showing how balance depends on their harmony. When one sense falters, the others can compensate. In space, vision becomes dominant. On Earth, the three share responsibility more equally. The ability to shift reliance demonstrates the resilience of the human nervous system. Space exploration also prompts questions about the future. As missions grow longer, lasting months or even years, how will prolonged absence of gravity affect the vestibular system? Will hair cells in the utricle and saccule change their sensitivity? Will the brain develop permanent new ways of interpreting vestibular input? What challenges will astronauts face when landing on other worlds, where gravity may be weaker than Earth's, but not absent, such as on the Moon or Mars? These questions highlight the importance of understanding balance, not only as a biological system, but as a foundation for human exploration beyond our planet. Animal studies in space have provided insights. Fish sent into orbit initially swim in looping, disoriented patterns, unable to distinguish up from down. Within days, they adapt, swimming normally despite the lack of gravity. Upon return to Earth, they must readjust once again. This mirrors human adaptation, showing that vestibular recalibration is a shared capacity among vertebrates. Other studies with rodents and amphibians reveal similar processes, with the brain adjusting to interpret vestibular signals differently in microgravity. These experiments demonstrate that the vestibular system is both ancient and flexible, able to serve life not only on Earth but in the unique environment of space. The vestibular system's role in space also underscores its connection to perception and emotion. Astronauts describe sensations of floating and drifting as both disorienting and beautiful. The loss of gravity changes not only balance but also the very experience of being embodied. Some report vivid dreams of motion, others a sense of freedom from weight. The vestibular system, though challenged, becomes part of a new way of perceiving the self in relation to the environment. It shows that balance is not merely mechanical but also experiential, shaping how we feel as much as how we move. As you imagine this now, picture the quiet chambers of the inner ear, organs that evolved to serve under Earth's constant gravity, now afloat in the silence of space. Their signals, once clear, become ambiguous, yet the brain listens, adapts, and finds new meaning in them. Orientation is redefined, balance recalibrated, life continues, steady even without the anchor of gravity. This is the resilience of the vestibular system, its ability to guide not only in familiar conditions but also in the most unfamiliar environments humanity has ever entered. And so, balance in space is a story of both disruption and adaptation. It begins with dizziness, with conflict between senses, with nausea and uncertainty, but it ends with adjustment, with harmony restored, with the body learning to trust new cues. The vestibular system, though challenged, does not fail. It bends, it shifts, it adapts, and in doing so, it reveals the remarkable capacity of humans to find stability, even when the very ground beneath them is gone. As this part closes, let the thought settle that balance is not bound only to Earth. It is a sense that can travel with us, adapting as we go, steadying us not only on land and sea but also in the quiet reaches of space. In that constancy lies reassurance, the knowledge that wherever we journey, the sense of balance will remain, always adjusting, always guiding, always present as a companion in motion and in stillness alike. 16. Common balance challenges. Although the vestibular system is remarkably steady and reliable, there are times when it can be disturbed. These disturbances are not unusual, and many people experience them at some point in life. They range from brief moments of dizziness to ongoing conditions that require care. Speaking of these challenges gently, with calm reassurance, allows us to see them not as threats, but as reminders of how delicate and sensitive balance truly island. By understanding them softly, we can appreciate both the fragility and the resilience of the vestibular system. One of the most familiar balance challenges is vertigo, the sensation that either the body or the world around it is spinning. Unlike ordinary dizziness, which may feel like lightheadedness or unsteadiness, vertigo is distinctive because it carries the illusion of rotation. People experiencing it may feel as though the room is moving, even though it is not. Vertigo can arise for many reasons, often linked to small disruptions in the inner ear. Although it can be unsettling, it is usually temporary. The very sensation of spinning is evidence of how active and precise the vestibular system is, responding strongly even to small irregularities. A common cause of vertigo is a condition called benign paroxysmal positional vertigo, often shortened to BPPV. The name may sound complex, but the idea is simple. Inside the utricle and saccule are tiny calcium crystals, the otoconia, that normally sit in place, shifting gently with gravity. Sometimes these crystals become dislodged and drift into the semicircular canals. When this happens, certain head movements cause them to move in the canal fluid, bending the hair cells in ways that send unusual signals to the brain. The result is sudden, brief spells of vertigo, often triggered by rolling over in bed, bending down, or looking upward. While the sensation can be strong, it is not dangerous, and with time or gentle exercises, guided by healthcare providers, the crystals can often be repositioned. This condition shows just how much depends on the tiny structures within the inner ear, and how even small changes can ripple outward into perception. Another common balance challenge is labyrinthitis, an inflammation of the inner ear that can arise after infections. When the delicate tissues of the labyrinth are irritated, signals to the brain may become distorted, leading to vertigo, nausea, and difficulty maintaining equilibrium. Labyrinthitis can also affect hearing, since the cochlea shares the same space as the vestibular organs. Most cases resolve with rest and care, leaving the balance system intact. Again, the temporary disruption highlights the sensitivity of the vestibular system, its ability to signal the brain immediately when something is amiss. Vestibular neuritis is similar, but in this case the inflammation affects the vestibular nerve itself. The nerve, which carries balance information from the inner ear to the brain, may send abnormal signals when irritated. This too can cause vertigo and unsteadiness. As with labyrinthitis, recovery is common, and the brain often learns to compensate for lingering changes. These conditions remind us that the vestibular system is not isolated but connected to broader bodily health, sometimes influenced by illnesses that touch many systems at once. Meniere's disease is another condition that affects balance. It is associated with episodes of vertigo, often accompanied by hearing changes and a feeling of fullness in the ear. Though the exact cause is not fully understood, it is thought to involve fluid imbalances within the inner ear. The episodes may come unpredictably, but between them, balance often feels normal. While Meniere's disease can be challenging, it is another example of how balance, hearing, and fluid regulation in the inner ear are deeply intertwined. The inner ear is a small space, yet tiny changes in pressure or fluid levels can alter both sound and motion perception. As people grow older, balance challenges often become more common. The hair cells in the inner ear may decline in number, reducing sensitivity. The nerve pathways may transmit more slowly, and the brain's ability to integrate signals may weaken. At the same time, vision may diminish, and proprioception may be affected by stiffening joints or reduced muscle strength. The combination can lead to unsteadiness and a higher risk of falls. Yet even here, adaptation is possible. Exercises that strengthen the legs, improve posture, and challenge balance can help maintain stability. Practices like Tai Chi and yoga emphasize slow, controlled movements that gently train the vestibular system and the body to work together. These adaptations show that while balance may change with age, it can still be nurtured and supported. Migraine is another condition sometimes linked with vestibular symptoms. Some people experience episodes of vertigo as part of a migraine pattern, even without the typical headache. Known as vestibular migraine, this condition highlights the connections between the balance system and other brain processes. The brain is an integrated whole, and changes in one part can ripple into others. Though disorienting, vestibular migraine is another reminder of how closely balance is tied to broader neurological activity. It is also worth noting that balance can be affected by factors outside the vestibular system. Low blood pressure, dehydration, fatigue, or certain medications can cause dizziness or lightheadedness. These sensations, though not always vestibular in origin, interact with the same perception of equilibrium. The brain blends all sensory input, and when one part falters, the experience of balance can feel altered. In these cases, restoring hydration, adjusting medications, or simply resting can often bring relief. Across all these challenges, one theme remains constant: the resilience of the balance system. Even when disrupted, the vestibular organs and the brain have a remarkable ability to adapt. If one ear is affected, the other can often compensate. If certain signals are weakened, vision and proprioception can take on greater roles. The nervous system is not rigid but flexible, capable of reweighting its inputs to maintain stability. This adaptability is what allows people to recover from vestibular disturbances, to regain balance after illness, and to continue moving with confidence. To think of balance challenges in this way is to see them not as frightening but as reminders of the sophistication of the system. Dizziness and vertigo are signals, not dangers in themselves. They show us that the vestibular system is alert, sensitive, and responsive. They remind us how much depends on tiny structures within the inner ear, structures that serve faithfully through years of life, and they highlight the importance of care of rest, of gentle exercise, of attention to health and supporting balance across time. As you rest now, it may bring comfort to know that even when balance falters, it often returns. The system is designed not only for sensitivity but also for resilience. Each episode of dizziness passes, each challenge invites adaptation, each disruption is met with recovery. The constancy of balance far outweighs its interruptions, and through it all, the vestibular system remains a quiet companion, always striving to steady the body, always seeking harmony, always guiding you back to calm. 17. Supporting vestibular health. The vestibular system, though hidden deep within the inner ear, serves faithfully throughout life. It allows the body to move gracefully, keeps the world visually steady, and reassures us of our orientation, even in darkness or stillness. Like all parts of the body, it can be nurtured, cared for, and supported. Though we cannot see the tiny semicircular canals, the utricle, the saccule, or the delicate hair cells that reside within them. To support vestibular health is not a matter of extraordinary effort, but of small, gentle practices that strengthen balance, preserve stability, and allow the system to work with ease. Movement itself is one of the most important supports for the vestibular system. When the body moves, the vestibular organs are engaged. Walking, turning the head, bending, and stretching all stimulate the inner ear, keeping it active. A life without movement can leave the system less responsive, while regular activity encourages it to remain sharp. Walking across a room, strolling through a park, or climbing a gentle hill, all of these simple motions are exercises in balance. Each step sends signals through the vestibular nerve, training the brain to interpret them and to coordinate with vision and proprioception. In this way, daily motion is not only a physical activity, but also a form of nourishment for balance. Head movements are especially helpful. The semicircular canals respond to rotations of the head, and when we move our heads gently in different directions, we stimulate them. Looking from side to side, nodding up and down, or tilting the head softly are natural ways to keep the canals active. These movements are part of daily life, but they can also be practiced deliberately, as in stretching exercises or slow, mindful motion. By encouraging the canals to respond regularly, we help the brain stay attuned to changes in position. Posture also plays a role in vestibular health. Standing upright, sitting tall, and aligning the head over the shoulders all provide the body with stability. Good posture allows the vestibular system to work in harmony with proprioception, reducing strain on muscles and joints. When posture is poor, balance can feel less certain, and the body must work harder to remain steady. Simple awareness of posture, practiced throughout the day, supports the balance system by giving it a stable foundation upon which to operate. Gentle physical practices such as yoga and tai chi are especially supportive. These traditions emphasize slow, deliberate movements, often carried out with attention to breath and alignment. In yoga, poses such as tree pose or warrior require balance, training the vestibular system to adapt to different positions. In tai chi, flowing sequences of motion challenge balance in subtle ways, encouraging coordination between vestibular input, vision, and proprioception. These practices are not about speed or force, but about steadiness, making them particularly beneficial for balance across all ages. They also provide calm for the mind, linking balance of body to balance of spirit. Strengthening the muscles of the core, legs, and ankles also helps support balance. The vestibular system provides information, but it is the muscles that carry out the adjustments needed to stay upright. Strong muscles respond more effectively to the brain's signals, correcting posture quickly and efficiently. Activities such as gentle resistance training, climbing stairs, or standing on tiptoes can all contribute to this strength. Even simple habits, like rising from a chair without using the hands or balancing on one leg briefly, encourage both muscle strength and vestibular engagement. Vision, though separate from the vestibular system, works closely with it, and caring for vision is another way of supporting balance. Clear sight helps confirm orientation, providing external references for the vestibular organs. Regular eye care, reducing strain, and practicing awareness of the environment contribute to stability. Similarly, proprioception supports vestibular function, and activities that enhance body awareness, such as mindful walking or stretching, strengthen the partnership between senses. Another aspect of vestibular health is gradual exposure to motion. The system adapts when it is gently challenged. Children often spin, swing, and climb, testing their balance and building resilience. Adults, too, can benefit from mild motion experiences, Whether it is riding a bicycle, walking on uneven ground, or practicing balance exercises, by encountering small challenges, the vestibular system learns to respond flexibly, reducing the intensity of dizziness in unexpected situations. This is why rehabilitation for vestibular conditions often includes controlled motion exercises. The brain can adapt, but it must be given the opportunity to practice. Lifestyle habits also play a role. Adequate hydration helps maintain the fluid balance within the inner ear, supporting its function. Restful sleep allows the nervous system to process and integrate signals, keeping reflexes sharp. Avoiding excessive noise protects the delicate hair cells shared between hearing and balance. Limiting substances that affect the inner ear, such as excessive alcohol, also helps preserve vestibular health. These small, steady choices provide long-term support for balance. Calmness itself can be a form of support. Stress and anxiety often heighten awareness of dizziness, making sensations feel more pronounced. By practicing relaxation, whether through breathing, meditation, or gentle activity, the nervous system remains steady, and vestibular challenges feel less overwhelming. Balance is not only physical but also emotional. A calm mind complements a steady body, allowing the vestibular system to work in harmony with the whole being. For older adults, supporting vestibular health becomes especially important. As sensitivity may decline, exercises that challenge balance gently help maintain function. Standing on one foot, walking heel to toe, or practicing slow turns can all be helpful. Group activities such as Tai Chi classes also provide motivation and enjoyment, reinforcing balance while fostering community. The message is not that decline is inevitable, but that care and practice can sustain balance well into later years. Supporting vestibular health also means listening to the body. If dizziness occurs, pausing, resting, and moving gently allow the system to recover. If challenges persist, seeking guidance helps prevent further disruption. Awareness and care, rather than neglect, are the foundation of vestibular support. Ultimately, supporting vestibular health is not a separate task to be added to life, but something woven into ordinary routines. Walking, stretching, maintaining posture, caring for vision, resting well, each of these everyday actions contributes to balance. The vestibular system asks for no extraordinary attention, only that we live with movement, care, and steadiness. In return, it provides stability for all our days, a quiet service that never rests. As you lie still now, know that you are already supporting vestibular health simply by breathing calmly, by letting the body rest in alignment, by giving the nervous system time to replenish. Each gentle habit of care adds to this support, ensuring that balance remains not only today, but through the years to come. The vestibular system, hidden though it is, responds with gratitude to this care, continuing its tireless work, keeping you steady in motion and at peace in stillness. 18. Training balance. Though balance works quietly in everyone, adjusting automatically in daily life, it can also be trained, refined, and strengthened. Dancers, athletes, acrobats, and performers all devote hours to developing balance beyond the ordinary. Their movements reveal what the vestibular system and its partners are capable of when practice shapes them into instruments of grace and precision. Yet training balance is not limited to experts or professionals. Anyone can gently cultivate balance, improving stability, coordination, and confidence. To explore the ways balance is trained is to see how the vestibular system, together with vision, proprioception, and muscle control, can be sharpened through experience. Dancers offer one of the clearest examples of balance training. Ballet, for instance, requires spinning on one foot, holding still in delicate poses, and shifting weight fluidly from one side to the other. To accomplish this, dancers rely on the vestibular system's ability to detect head movement and on vision to stabilize orientation. A technique called spotting illustrates this partnership. When performing turns, dancers fix their gaze on a single point, holding it until the last possible moment, then quickly snapping the head around to refocus on the same spot. This reduces dizziness, allowing them to spin many times without disorientation. Spotting is not a trick, but a training of the vestibular and visual systems to work together, to recalibrate constantly while the body rotates. Over years of practice, dancers develop extraordinary control, turning with apparent effortlessness, their balance seemingly unshakable. Athletes, too, show the results of balance training. Gymnasts walk across beams only inches wide, flipping and turning with precision. Their vestibular systems detect every rotation, while proprioceptors in their muscles signal the tension and stretch required to land safely. Skiers carve paths down mountains, leaning into curves with exact timing, relying on vestibular input to sense tilt and acceleration. Surfers ride waves that shift beneath them, their balance continuously adapting to moving water. In each of these activities, balance is not passive but active, challenged and refined by practice. The brain learns to interpret vestibular signals more accurately, to integrate them more quickly with visual and proprioceptive cues, and to command muscles with greater efficiency. Training balance often involves deliberate challenges to stability. Athletes may practice on unstable surfaces such as balance boards, foam pads, or wobble discs. These tools exaggerate sway, forcing the vestibular and proprioceptive systems to respond more strongly. Over time, the brain becomes more skilled at making rapid corrections. This principle extends to daily life as well. Walking on uneven terrain, such as grass, sand, or gravel, gently trains balance. Hiking on trails, climbing stairs, or even standing on one foot while brushing teeth are simple ways of encouraging adaptation. The vestibular system thrives when engaged, responding to new demands by becoming more precise. Martial artists train balance in another way, blending posture, motion, and awareness. Many forms of martial practice emphasize rootedness, the sense of being stable and grounded, even while moving quickly. Stances are practiced until they become second nature, allowing the body to remain balanced while executing strikes, blocks, or evasions. The vestibular system contributes by signaling orientation, while proprioception ensures that weight is distributed evenly. Martial artists also train in environments where balance is challenged deliberately, such as sparring, where sudden changes test stability. Through repeated exposure, the brain learns to remain calm and steady, even when external forces try to disturb equilibrium. Balance training is not limited to the young or to professionals. Older adults, too, can benefit from exercises that nurture balance. Programs often include simple tasks: standing with feet together, then with one foot in front of the other, then on a single leg. These exercises gently stimulate the vestibular system and strengthen the muscles that respond to its signals. Walking heel to toe along a straight line, turning the head while walking, or practicing slow bends and reaches are additional ways to support balance. Such training reduces the risk of falls, but it also improves confidence. To feel steady is to move with assurance, and this calm confidence enriches daily life. The vestibular system's adaptability is central to all balance training. When exposed to repeated challenges, the brain learns to interpret signals more effectively. Dizziness that once accompanied spins becomes less intense. Sway that once felt alarming becomes manageable. This process is sometimes called habituation, and it is used in vestibular rehabilitation for people with balance disorders. By gradually exposing the system to controlled motion, therapists help patients reduce symptoms and regain stability. This principle is mirrored in the training of dancers and athletes, who expose themselves to demanding movements until the brain adapts, transforming difficulty into grace. Even playful activities serve as balance training. Children balancing on curbs, climbing playground structures, or rolling down hills are not only enjoying themselves but also strengthening their vestibular and proprioceptive systems. Games that involve hopping, skipping, or spinning provide natural challenges that build coordination. The laughter and joy mask the serious work being done beneath the surface, as the brain calibrates itself for stability. Play, in this sense, is one of nature's original training grounds for balance. Breath and calmness also support balance training. Practices such as yoga or tai chi integrate controlled breathing with movement, encouraging relaxation while challenging posture. When the body is calm, the vestibular system works more smoothly, free from the amplifying effects of anxiety or tension. Training balance in this gentle way emphasizes not only physical stability but also inner steadiness. The result is harmony between body and mind, a steadiness that extends beyond movement into daily life. Technology has also found a role in balance training. Virtual reality and motion platforms can simulate challenging environments, giving athletes and patients alike opportunities to practice in safe conditions. For example, simulated boat decks or moving floors allow the vestibular system to be challenged without risk. These tools demonstrate how modern methods can extend natural training, always with the same goal: to strengthen the dialogue between vestibular input, vision, proprioception, and muscular response. At the heart of all balance training lies the principle of attention: to focus on posture, to notice sway, to practice stillness, or to attempt new movements, all require awareness. This awareness itself strengthens balance, for it brings conscious cooperation to a system that usually works unconsciously. Over time, the conscious effort fades, and steadiness becomes natural again, now reinforced by practice. This transformation from effort to ease is the essence of training. As you consider this now, imagine the many ways balance is trained across life. The dancer spinning gracefully, the athlete landing a jump, the older adult practicing calm movements, the child balancing playfully on a curb. All are examples of the vestibular system growing stronger through use. Each challenge, whether playful, artistic, or practical, encourages adaptation. The vestibular system is not a rigid mechanism, but a responsive partner, always ready to learn, always capable of refinement. And so, training balance is not only about performance, but about well-being. It enriches life with stability, reduces fear of falling, increases confidence in movement, and deepens the connection between body and mind. Whether through art, sport, play, or gentle practice, balance training supports not only the vestibular system, but the whole of human experience. As this part draws to a close, let the thought settle that balance can be nurtured. It is not fixed, not fragile, but adaptable. With each movement, each challenge, each gentle practice, the vestibular system grows stronger, steadier, more resilient. And in that resilience lies calm, the calm of knowing that the body is supported, that steadiness is possible, and that balance, once trained, will always be there to guide you in motion and in rest. 19. The vestibular system and relaxation. Balance is often thought of as something that allows us to move, to walk steadily, to run smoothly, or to spin without falling. Yet balance is just as important in moments of stillness. The vestibular system not only supports motion but also provides the foundation for rest. It reassures the body that it is safe to lie down, to close the eyes, and to let go into sleep. Without its steady guidance, stillness would not feel calm. The body might sense falling, even when it was at rest, and relaxation would be elusive. To reflect on the vestibular system's role in relaxation is to see how deeply balance is tied not only to action but to peace. Every time you lie down, the vestibular system confirms the change. The otolith organs, the utricle and saccule, detect the shift as the head and body tilt into a horizontal position. Their tiny crystals move gently, signaling the brain that gravity is now pulling differently. The brain interprets this without effort, understanding instantly that the body is resting flat. This awareness prevents the sensation of falling. It allows the muscles to release tension, confident that orientation is secure. Without this signal, lying down might feel uncertain, as though the body were floating or tipping. With it, rest becomes natural. Even small adjustments during rest are guided by the vestibular system. When you roll from one side to the other in bed, the semicircular canals detect the rotation. The otolith organs confirm the tilt, and proprioceptors in the muscles and joints report the change in posture. Together, they tell the brain that the movement has occurred smoothly and safely. This constant feedback is what allows you to shift positions in the night without waking fully, to move in dreams without startling the body into alertness. The vestibular system watches over these transitions, keeping orientation clear even in sleep. The connection between balance and relaxation is also seen in rocking. From infancy, gentle rocking has been a universal way to soothe. Parents sway babies in their arms, cradles are designed to rock, and even adults often find rocking chairs calming. The vestibular system is the reason this works. Rhythmic, gentle motion stimulates the semicircular canals and otolith organs in a way that reassures the brain. The steady, predictable pattern of movement becomes soothing, lulling the nervous system into calm. It echoes the sensations of the womb, where balance was first formed, and it provides a quiet rhythm that encourages rest. Dreams, too, reveal the link between vestibular sensation and relaxation. Many people have experienced the sensation of falling in a dream, followed by a sudden jolt awake. This may reflect the brain interpreting vestibular signals in sleep, weaving them into dream imagery. But more often, vestibular input during sleep is peaceful. Floating, flying, drifting, these are common dream experiences, gentle reflections of the balance system at rest. They show that even in unconsciousness, the vestibular system shapes perception, contributing to the inner calm of the sleeping mind. Relaxation is not only physical but also emotional, and the vestibular system plays a role here as well. The brain regions that process balance are connected to those that regulate emotion. When balance is secure, the nervous system interprets this as safety. When balance is disrupted, as in dizziness, the body may feel anxious or uneasy. This is why calmness of balance supports calmness of mood. Practices that strengthen balance often also reduce stress, not because they directly alter thoughts, but because they provide a foundation of stability. To feel steady is to feel safe, and to feel safe is to relax. Meditative practices sometimes draw attention to balance without naming it. Sitting upright with eyes closed, focusing on the breath, practitioners rely unconsciously on vestibular input to remain steady. The sense of verticality, of stillness, of being grounded, all come from balance signals. Without them, meditation would feel unstable. With them, the posture can be held effortlessly, allowing attention to rest inward. Balance thus becomes the quiet foundation of mindfulness, enabling the body to be still while the mind grows calm. The vestibular system also plays a role in helping the body let go into sleep. As the day quiets and the body prepares to rest, the vestibular system continues its silent work. It confirms that the body is horizontal, that movements are small and safe, that no tilt threatens stability. This constant reassurance tells the nervous system that it can release vigilance. Muscles soften, breathing slows, and the body drifts toward sleep. Without balance, the transition might be troubled by uncertainty, but with it, the shift feels natural. The vestibular system is, in this way, a gatekeeper of rest. Gentle movements before sleep often enhance relaxation, precisely because they engage the vestibular system. A slow walk, a few stretches, or the rocking of a chair provide vestibular input that soothes the brain. These actions reassure the body of stability, preparing it for stillness. Even turning the head slowly or lying down with care engages the semicircular canals and otolith organs in calming ways. Each motion becomes part of a soft ritual that guides the body toward peace. Balance challenges, when present, can make relaxation harder. Vertigo or dizziness can intrude upon stillness, making it difficult to trust orientation. Yet even here, the resilience of the vestibular system shows itself. With gentle practice, with time, with exercises that retrain the brain to interpret signals, stability often returns. The nervous system seeks harmony, and even when disrupted, it finds ways to restore calm. This adaptability is itself a form of reassurance. The balance system is always striving to guide you back to steadiness, even if the path takes time. Animals demonstrate the calming role of vestibular input as well. Many species rock or sway to soothe themselves. Birds preen and sway gently on branches. Cats knead and shift rhythmically before resting. And even marine mammals drift in calming motions. These behaviors suggest that vestibular stimulation is universally linked to comfort. Across species, balance signals not only support movement, but also contribute to rest. As you reflect on this now, you might notice the feeling of steadiness beneath you. The surface supports your body, gravity anchors you, and the vestibular system confirms that you are safe and still. This quiet awareness is the background of relaxation. It allows you to release tension, to trust the body's position, to close the eyes without fear of disorientation. Balance does not intrude but supports, a gentle companion that makes rest possible. In the end, the vestibular system is not only an organ of movement but also an organ of calm. It steadies not just steps but also stillness. It reassures not just in action but in rest. Its signals, carried constantly to the brain, provide a foundation upon which peace is built. Without it, the world would feel uncertain. With it, life feels anchored, secure, and safe to let go. And so, as this part concludes, imagine the vestibular system as a quiet guardian of your rest. Its tiny crystals, its flowing fluids, its delicate hair cells, all are working even now, confirming your position, keeping you steady. They ask for no effort, they give without pause. Their constancy allows you to relax, to let go, and to drift gently into sleep. The vestibular system is, in every sense, a companion of relaxation, always present, always steady, always guiding you into peace. 20. Closing. Reflections on inner stillness. As we come to the final part of this gentle exploration, it is worth pausing to notice what has been present all along. From the very first moments of life, balance has been a companion. It has guided the smallest infant as they lifted their head, steadied the child as they took their first steps, and supported the adult in walking, running, resting, and dreaming. It has been present in motion and in stillness, in times of play and in times of rest, in waking and in sleep. And though we have journeyed through its anatomy, its pathways, its cooperation with vision and proprioception, its challenges, and its role in relaxation, balance itself has remained constant, always there in the background, always doing its work quietly. The vestibular system, hidden deep in the inner ear, is not something we can touch or see. Its hair cells, crystals, and fluids are invisible to the naked eye. Yet their signals shape the entire experience of living in a body. They allow the world to remain stable even as we move through it. They keep us upright against the pull of gravity, and they reassure us when we lie down that we are safe to rest. They are delicate, but they are also enduring, serving faithfully for years, often without notice. Their work is not dramatic but steady, a constant presence that supports life from within. Stillness itself is made possible by balance. To lie in bed, to sit in a chair, to meditate in calm, repose all depend on the vestibular system, confirming orientation. Without it, stillness might feel like falling, quiet might feel like drift, and relaxation might never arrive. With it, the body knows its place in the world, anchored to gravity, secure in space. This anchoring allows the mind to let go, to release tension, to trust in calm. Balance is, in this way, not only a physical sense but also an emotional foundation, shaping how safe we feel and how deeply we can rest. There is a kind of poetry in the vestibular system's dual nature. It is both active and passive, both watchful and quiet. It responds instantly to movement, detecting the smallest tilt, the faintest acceleration, the briefest turn of the head. Yet it is also constant, maintaining a background of signals that assure the brain of stillness. It is never silent, but its voice is always soft. Unlike vision, which fills the mind with vivid images, or hearing, which brings the sounds of the world, balance whispers rather than shouts. Its whispers are of gravity and space, of motion and rest, always present, always calm. Throughout history, humans have recognized the value of inner stillness. Philosophers have spoken of balance not only of the body but of the soul. Poets have written of harmony between the self and the world. The vestibular system, though biological, offers a reflection of these ideas. It provides literal balance, but in doing so, it also gives rise to the feeling of balance. When our bodies are steady, our minds can be steady too. The harmony of vestibular signals, vision, and proprioception becomes a metaphor for the harmony of life itself, where different parts work together to create stability. The connection between balance and peace can also be seen in nature. Animals find rest in positions that rely on their vestibular systems for security. Birds sleep perched on branches, trusting their balance to keep them from falling. Cats curl into balls, shifting until their vestibular sense assures them they are steady. Fish drift in water, oriented by otoliths that whisper of gravity even beneath the surface. Balance allows them all to let go, to surrender to stillness without fear. In this way, the vestibular system is not only human but universal, part of the fabric of life across the earth. In our modern lives, balance can be overlooked. We think of strength, speed, endurance, and agility, but balance feels less visible, less celebrated. Yet it is balance that underlies them all. Without balance, strength cannot be used, speed cannot be directed, endurance cannot be sustained, and agility cannot be expressed. Balance is the silent partner that makes all movement possible. It is the root from which other capacities grow. To honor balance is to honor the foundation upon which life's motions rest. As we close, imagine now the vestibular system within you. Picture the semicircular canals, curved arcs filled with fluid that shifts gently when your head turns. Picture the utricle and saccule, with their tiny crystals drifting subtly as gravity pulls them. Picture the hair cells, bending with each motion, releasing signals that travel along the vestibular nerve. Picture the brain, receiving these signals, blending them with vision and proprioception, creating a seamless sense of orientation. All of this is happening quietly, without effort, even now as you rest. It is happening whether you notice or not. whether you are in motion or still. It is the background of your existence, the silent thread that steadies your life. Reflect also on the resilience of this system. Though tiny, it adapts. Though delicate, it endures. It has guided you since before you were born, rocked gently in the womb, and it will continue to guide you in the years to come. It has allowed you to walk, to run, to dance, to sit, to lie down, to dream, and to sleep. It has faced challenges, moments of dizziness, spells of vertigo, the disorientation of sickness or fatigue. But it has always sought recovery, always worked toward harmony. It is a system built for steadiness, for adaptation, for life itself. And now, in this final reflection, let balance be not only a subject of thought, but also a felt experience. Notice the surface beneath you, how it supports your body. Notice the gentle pull of gravity, steady and constant. Notice the sense of orientation, of being upright or lying down, secure in space. These sensations are gifts of the vestibular system, always offered, always present. They are the foundation of stillness, the reason you can rest with confidence. As you drift further into calm, allow yourself to trust this system. It is working for you, as it always has, as it always will. It does not require your attention or effort. It is automatic, reliable, and faithful. In its constancy lies reassurance. In its quietness lies peace. In its balance lies your own stillness. And so this journey ends where it began, in quiet appreciation of the vestibular system, the hidden sense of equilibrium. It is a system of science, of anatomy, of physiology, but it is also a system of calm, of safety, of peace. To know it is, to see how deeply balance runs through life, shaping every movement and every rest. And to trust it is to find stillness within yourself, a stillness that anchors you, steadies you, and carries you gently into sleep.